A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm. Thank you. So, hello, a very warm good morning to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session of geography, where today we shall be talking about the portion of oceanography in further more detail. Now, yesterday, while we were talking about the portion of global climate, Indian climate, after that, we entered into the aspect of oceanography. And we had initiated the discussion with the ocean bottom relief features. And there, in the ocean bottom relief features, we had taken a look at the fact that you have varying kind of relief features which are created either due to tectonic events, volcanic events, or might even be erosional or depositional events that could also have led to the creation of the various landforms. Now, amongst the various things, we had taken a look at what do we understand by a continental shelf, what do we understand by a continental slope, where is it that we find a submarine canyon, and how is it that a submarine canyon is created. And there we had taken a look that in the case of submarine canyons, it can be created at the mouth of the large rivers because of the force that is exerted by the rivers. But at the same time, it also can get created due to erosional and depositional actions which are experienced. So those erosional and depositional events and actions can also initiate the formation of canyons. And there we took a look at what do we understand by the turbidity current. So today, we'll take a look at the other types of bottom relief features. And after that, we shall be moving on into the physical prospects and the physical aspects of water, where we shall be taking a look at the aspect of temperature, variation in temperature, where we are basically going to have an idea that how is it that temperature varies, not only across various latitudes in the ocean, but also across the depth of the ocean. And the same approach we shall follow in terms of the study of oceanic salinity as well. So, without further ado, let us initiate the discussion about the ocean bottom relief features, and we initiate the discussion from the deep sea plains. Now, when we say deep sea plains, very, very similar to the plain regions that you find across the land areas, in the sense that these are also flat and featureless. The average depth is between 3 to 6 kilometers from the surface. So you can imagine that at that particular depth, you have a vast expanse of plain which is in existence. Now, these deep sea plains, these are also what are referred to as abyssal plains. Abyssal plains. Now, at this particular depth, you don't have the availability of light at all. When we go to a depth of maybe 3 kilometers, 4 kilometers, 5 kilometers, 6 kilometers from the surface, you don't have any availability of solar insolation at that depth. So these areas are under permanent darkness. Overall, these are the regions which lie in what is referred to as aphotic zone. These are in permanent darkness. Now, if a region is in permanent darkness, obviously plants cannot grow there. You cannot have the plants because the photosynthesis cannot be carried out. So, for a long period of time, it was thought that there would be no civilization, or not civilization rather, there would be no habitation or no individual species would be found there. But later on, and eventually, we did find a lot of set of species living and sticking to the ocean bottom itself, and they have their own defined body morphology, or their body has been adapted for living in the ocean bottom, where they have been living for millions of years. Because at the ocean bottom, the condition has remained largely consistent for a very long period of time. So such kind of species which live in the ocean bottom, they are referred to as benthos or benthic species. Okay, right? So that is where these species are referred to as benthos or the benthic species in general. Okay, and they live in the ocean bottom. Now, the ocean bottom is largely comprised with, you will find many seamounts to be in existence. Other than that, you will find a lot of deposits, extensive deposits to be found across the various areas of the ocean bottom. That is something which can be thought to be a common phenomena here. Then you have a deeper part still. It is not as if these 3 to 6 kilometers depth, that is going to be the deepest portion of the ocean. No. Here, you will observe that you still have further deeper portions which are in existence. And that is what is referred to as the oceanic deep or trenches. The oceanic deep or trenches, the oceanic trench that we have, right? These can get as deep as 10 kilometers, even 10.5 kilometers from the surface. That is how deep it can get. Now, here we have seen that oceanic deep or trenches are created. Why? Because of convergence of plates. Convergence of plates. Okay? And not any and every kind of convergence will obviously create an oceanic trench. For an oceanic trench to be formed, you need either ocean-ocean convergence or ocean-continent convergence. So we have taken a look at few of the examples of of these trenches in the portion of map pointing. We have taken a look at them. For example, we have taken a look at, for the case of Kuril trench, Japan trench. You have the Sunda trench, Java trench, all these trenches, Mariana trench, the deepest trench across the entirety of the world, Peru Chile trench. So wherever you find the zones of convergences, you'll find a trench is created. These are very, very deep and narrow regions, and they have an unexpected kind of physical condition surrounding them. So these are your ocean bottom relief features. Now, you should be aware about the formation, how they are created, how they are formed. So continental shelf, depositional in nature; continental slope, erosional in nature; rise, again depositional in nature; submarine canyon, again erosional in nature; deep sea plains, depositional in nature; and oceanic trenches. Well, these oceanic trenches are created due to tectonic activities. In fact, even the deep sea plains, or anything for that matter that you consider, even deep sea plains at one point of time would have been created as a result of volcanic eruption. Just like how land masses are created on the planet, there also they would have been created. What we have studied in the entire process of seafloor spreading, that would have been the phenomena which would have driven the formation of deep sea plains. But over a period of time, there would have been a lot of deposits carried upon them. Okay, now this is the broader sketch. If you take a look at it, so basically, if you take a look at the formation, here you have the shelf area, here you have the slope, deep sea plain, you have a few islands, or the submerged ones will form the seamount, Then the oceanic trenches. How deep can it go? Right? So that is basically the case of various different portions of ocean bottom relief feature. Now, after this, we take a look at the physical properties of water and physical properties of oceanic water, that is oceanic temperature. Now, when we talk about the aspect of oceanic temperature, here we shall be analyzing about what is the factor which relates to temperature, how is it that the temperature varies, and what are the various different instances of variation in temperature, and eventually we'll get an idea about the impact of that as well. How convergence creates trenches. We have covered it in very great detail, Anthony, in the portion of plate tectonics. Kindly take a look into the portion of plate tectonics. I'm sure you will be able to access the recorded videos now that the recorded videos are available. So you will always be able to take a look at that how, in the case of a continental oceanic convergence, you have an oceanic trench, how in the case of oceanic convergence also you have the oceanic trench. Kindly take a look into geomorphology, you'll get an idea, and a detailed idea for that matter. What are benthos species? Benthos species are basically to be found at the ocean bottom at a depth where you will not have the presence of light. You have immense amount of pressure which they face. The pressure at the ocean bottom is very, very high, and it is almost equal to around 6 to 8 tons per square centimeter. So you can think about that in 1 square centimeter, the amount of pressure which is exerted. So in that high pressure, you have the species which are adapted to living in that. For example, you have overfish, certain types of sharks, etc. So that is what is benthos. Okay, and then after that, Shabir, what is your question? Volcanic arc, trench, island, all those are inside the ocean. Trench is inside the ocean. When we say an arc or an island, island is sometimes comes up in all the cases. Whenever you refer to the term island, island will come above the surface, and arcs, they can have sea mounts and islands included in that case. Deposition, as I told Rahul just now, that deposition does not create deep sea plains. Deep sea plains are created just like any landmass is created, but over a period of time, there is a lot of various deposits carried out by or the sand or the mud and the ooze. So that in a way constitutes the ocean floor or the deep sea plain in that matter. Total solar eclipse. Kishan, your question, first of all, is not clear and very out of context. What is the difference between a continental rise and a continental slope? Continental slope will have an erosional feature. It will be very steep. And then at the foot of that continental slope, you will have depositions which are carried out. And that is what is referred to as a continental rise. Kishan, why total solar eclipse are rare in some places? Understand why you have total solar eclipse. First of all, very basic, understand why is it so, and secondly, understand the kind of tilt that the earth's axis creates. So in a way, you can only have limited, and moon is not so big to cast the entire shadow across every part of the planet. It will have a smaller portion. So in the tilt that the planet has, the shadow exists in some region, the planet rotates, obviously it cannot have the shadow across the entirety of the planet. So that is why you'll find a curvilinear path of the regions impacted by total solar eclipse. Shabir, that is not a question that you have. Okay, if you have a question, guys, please don't vitiate the meaning of a question. Please conclude class on 9:30, because at that time I reached at my school, and that after that I am not given proper attention because school morning assembly is starting. So if the attention right now is whether I have to join the assembly or not, then I won't address this question, basically. And if you want me to address whatever the answer you want me to give, I am ready to give that. Write that this is the answer I seek. I'm ready to read that answer out. How do the species get oxygen? Is oxygen present at such depth? Oxygen is dissolved in water at such depth, and that is how the species get that oxygen. Seamounts are created, Anil, as a result of volcanic eruption. June, Pulkit, we had talked about it yesterday also, that June, there is a cyclonic disturbance developing around the region of Arabian Sea, because till now you had the ITCZ still lagging over the portion of the Arabian Sea. So you had the pre-existing low pressure. And on top of that, Arabian Sea has gotten heated up much more and much significantly over the past couple of months due to the dry season which has prevailed around, whereas the northern part of India has remained comparatively cooler because of increased amount of rainfall in the month of May, due to which the ITCZ has not transferred to the north to such a decisive extent. Okay, now after this we come to the portion of oceanic temperature. Now oceanic temperature here, what is the prime source of heating when we talk about the oceans? Now, in the case of the oceans, the prime source when we talk about the heating is the solar insolation. Okay. The solar insolation, that is the prime source of heating. And that is why, in general, you will find that the surface gets heated quite significantly, and the lower regions, they get heated at a slower pace. Okay, so that is why you will find that the surface gets heated significantly more. Now this solar insolation is the source of heating. So here we also have to understand that that is not the only factor which will determine the oceanic temperature. In general, even across the similar latitudes, we have seen in the case of the Pacific that the oceanic temperature tends to vary sometimes. For example, during Walker circulation and La Nina cycle, we have seen that you have warmer temperatures in the region of the Western Pacific. Whereas in the case of El Nino, you have warmer temperatures across a similar latitude in Eastern Pacific. So you have a lot of factors which contribute to heating and cooling of the water bodies or the oceans. So here, that is what you have to understand, that what are the factors which contribute to the variation in temperature. The first factor is the factor of latitude, the latitudinal extent of any water body, across which latitude does that water body lie. So here you can have, for example, the region of northern Atlantic or northern Pacific. They will never have the same temperature as the region of, let's say, equatorial or tropical Pacific. So always with the variation in latitude, there is a variation in terms of heating or cooling. Now in this case also, if you think about the northern hemisphere and simultaneously consider the southern hemisphere, where is it that you will think that there is a uniform variation in temperature in terms of the water body? Always in the case of southern hemisphere. Latitudinal extent or the latitudinal variation in temperature is much more clearly defined, is much more apparent in the southern hemisphere. And why is that? That is because you have a uniformity of water body, you have a large and a major dominance of water body which is present. So that is why that has got a kind of a uniform variation. Then we have unequal distribution of land and water. Now, unequal distribution of land and water means that wherever you have predominantly land as a feature which is present. In that area, the heating of the land or the cooling of the land can also induce a change in temperature of the water body. If the land gets very heated up, the surrounding water body will also get heated up. If the land gets very cooled down, the surrounding water body will also get very, very colder. So that is where, when you have the unequal distribution of land and water, it brings about a variation in temperature. This is the reason why you will observe that northern hemisphere, because it has got greater contact with land compared to the southern hemisphere, has more heat which is received. Why? Land heats up faster. That is why land heats up at a much faster rate. Then you have the prevailing winds. Prevailing winds means existent winds, the winds which are already in existence. So we have, under prevailing winds, we consider generally the permanent wind system, isn't it? We consider the permanent wind system, existent permanent wind system. Okay. Now, that when you see the existent permanent wind system here, it can be onshore or offshore. And we have seen that when you have onshore winds, whenever in any region, let's say if this is the water body and if this is the land area, if you have the onshore winds, that leads to the piling up of water, and water eventually is forced down, what we experience as downwelling. And whenever you have downwelling, what happens to the sea surface temperature in those areas? When you have downwelling, what is the resultant of it? Very good. Beautiful. So downwelling results in rise of temperature. Sea surface temperature. Simultaneously, in areas where you have the wind which is offshore in general, in those areas, as the top surface is carried away by the wind, the subsurface is brought up. The subsurface water comes up. So that is the upwelling. And upwelling, what it does is it decreases the temperature. UPSC has asked a question about this in the prelims examination from the very basics, and it has repeated it almost twice, I think, where it has asked about what is the temperature variation, or the eastern part of the ocean will be warmer or the western part. So eastern and western part of the ocean and eastern and western part of the continent, kindly don't end up getting confused in that. Okay. Now, the other factor contributing to the temperature is the role played by ocean currents. Now, the role played by ocean currents in modifying the ocean temperature is very similar to the role played by advectional process. We have seen, excuse me, Nadeem, you can actually do that. You can take a look at the previous lectures. It will be easier. When air move land to water, it is offshore. Yes, that is correct. So now we come to the role played by ocean current in terms of modifying the temperature. Here, You have to understand that ocean current is basically a unified, directionalized motion of water in the oceans, just like the rivers in the oceans, if you can imagine something like that. They end up moving water in a definite direction. Now, they can be warmer, they can be colder. If the ocean current is coming from higher latitude, it is generally colder. If the ocean current is coming from lower latitude, it is generally warmer. So here, these ocean currents, the role that they play in influencing the temperature is almost similar to that of advection. Colder ocean currents cool down an area, bring colder temperature conditions, whereas warm ocean currents, they will warm up an area, bringing about warmer conditions in that region. We'll take the example of it. For example, if you consider the northern portion of Europe, if you can take a look at the map, I'll show you the map here. Observe this portion, this particular portion. That is the Kola Peninsula. This is what is regarded as the Kola Peninsula. Now, near Kola Peninsula, you have the port city of Murmansk, right? Port city of Murmansk is situated there. And ideally, at these high latitudes, everything would get frozen, right? During most of the year, everything would get frozen. But in this case, this particular region remains ice free because you have a warm ocean current coming through this area, and that is the North Atlantic drift. So you have a warm ocean current, that is North Atlantic drift. That North Atlantic drift is the warmer one, and that is why Murmansk tends to remain ice free for majority of the year, allowing trade and other purposes, and the port remains free. This is why at the time of the erstwhile Soviet Union, Murmansk would serve as a very important base in terms of the Soviet Navy, and more in particular the submarine force of the Soviet Navy, the nuclear armed submarines, and the nuclear submarines in general, they would be deployed in the region around Murmansk. Now, that is the factor of ocean current. So here you can write as an example North Atlantic drift, drift being warmer. And don't worry, guys, we'll cover the ocean current in significant detail. So don't worry. This is just a mention of it. Being warmer makes water in higher latitudes ice free for most of the year. Okay, so that is the example. Just remember, for simplicity, role is same, similar to the process of advection. Role is very similar to the process of advection in general. Now, then we have the factor of open seas versus enclosed seas. What does this mean? This basically ends up indicating a variation in temperature when you consider a water body like an ocean, or a water body like a Black Sea, Mediterranean Sea, Baltic Sea, any of those. So When we consider open seas here, that refers to oceans, right? And enclosed seas, example, Black Sea, Mediterranean Sea, Baltic Sea, etc. These are enclosed. Now here, the difference in temperature which will be experienced purely based upon what is the rate of heating, what is the rate of cooling. We know that when we consider an open ocean, a large area of the oceanic region, the change in temperature basically is very, very gradual. Because in the oceans, here, heating and cooling of the water body, that will take its own set amount of time. So oceans will get heated and cooled down in their own set time. Whereas when we talk about the enclosed sea, the influence of the surrounding land areas is very significant and very pertinently felt over these waters. For example, consider this Red Sea, this particular region, that is the Red Sea. Let us consider this. Now, Red Sea is very closely surrounded by land masses. Now, as the land masses they get heated up, Red Sea will also get heated up, isn't it? So, when compared with Atlantic Ocean at the similar latitude, which will be warmer, Red Sea or Atlantic? Always, you'll find that the Red Sea is much more warmer. Yes, good. You'll find that the Red Sea is warmer. Why? Because the land is getting much hotter. Whereas, let us consider a region such as Baltic Sea in the northern latitudes or the higher latitudes. Now, here again, when you talk about higher latitudes, the land areas they will get very, very cold very fast. Whereas the water bodies they will take their own good time in cooling down and losing the heat. So, if you consider any area in the Atlantic Ocean at a similar latitude and compare the temperature of that enclosed sea, that is the Baltic Sea, where do you think it will be colder? It is the Baltic Sea, which will be much more colder, isn't it? So, because it is surrounded by land areas which will cool down very quickly. So, that is why at low latitudes, enclosed seas, they have enclosed seas, that is the ones which are surrounded by land. So, they will have higher temperature. Okay. And why is that? Because the land influences the heating. Whereas at higher latitudes, you have the open seas, that is the oceans. Open seas here indicates the oceans. So the oceans have higher temperature and enclosed seas are much colder. Okay. So this is another influence that you experience in case of ocean temperature. So this is the variation in temperature that you will experience here. Observe that around the region of the equator and the tropics, observe that the waters, they are really warmer. And here if you observe the region of Bay of Bengal, compare it to the region of the Arabian Sea, you'll find that Bay of Bengal is very, very narrow, right? Surrounded by land, much more significantly at a closer proximity. What does that mean? That virtually means that there's a greater probability of Bay of Bengal heating up much sooner as compared to the Arabian Sea, because the Arabian Sea is much wider. So if the region of Bay of Bengal gets heated much more quickly, that means greater probability of tropical cyclones happening in Bay of Bengal. Now here, if you observe carefully, I want you to notice the slight trend here. observe the water in the region of equatorial Atlantic. The water in equatorial Atlantic. Observe the shape of this carefully. Now, when you take a look at this, what impression does it give you? It will give you an idea that this water is basically flowing, isn't it? Around the equator and then spreading out, isn't it? So that is basically how eventually when we come to the portion of ocean currents, we will take a look at it, that how warming up of the water or rise in temperature in any region can lead to the induction or the formation of an ocean current. Here also, you will observe that the water in general in the Western Pacific is much warmer. Now, more importantly, if you observe the latitudinal variation of temperature, you will observe that in this region of Southern Hemisphere, you have a much uniform variation in terms of temperature. So, all these are basically the factors determined by and what end up determining the horizontal distribution of temperature. Now, we take a look at how is it that the temperature varies as you start moving at the depth. Okay, so how is it that the temperature varies, the vertical variation? So solar insolation is the main source of heating of the water. The solar insolation and the heat and the energy received by the sun is the main source, but that heat and energy or solar light even would not be able to light up the entire ocean. Beyond few hundred meters, that solar insolation is not even available. Solar insolation will be available only in the top few layers. And the region where the solar insolation is available, that is referred to as the photic zone. That means availability of light. Availability of light. Now, this will extend for a few hundred meters, maybe 300 meters, 400 meters in certain cases at max. Now, availability of light means what? Means you will have the variation in terms of the plant life also. You will have a lot of plants which will exist in that area. Why? Because then they can carry out photosynthesis. Light is a very important factor for contributing to photosynthesis. So here you will always end up finding greater biodiversity. Greater biodiversity. When we go beyond a certain depth, the sunlight is not able to reach. Okay, that is why at deeper depths it is permanent darkness. There is no availability of sunlight. There is perpetual darkness, right? So that is what is referred to as the aphotic zone. No sunlight available. The changes that it brings in diversity, biodiversity, the adaptations that the biodiversity goes through, all of that we will cover, or you will cover whenever you attend the session of environment ecology, that what are the adaptations that the species have to go through to survive in this area. But here, while we concentrate upon the variation in temperature, here it is important for us to imagine that what is going on. So for example, let's suppose this is the water body. Let's suppose this is the bottom of it, the depth. Now, when the solar rays they come through, those solar rays, They will heat up the surface very significantly. The surface will immediately gain a lot of temperature. But then, slowly and steadily, the strength starts to weaken of the solar rays as it enters into the water. The strength starts to weaken. Eventually, by a depth of around 400 to 500 meters, that is where the solar rays will be available. Beyond that, no solar rays, permanent darkness. So, what will be the variation in terms of temperature? How is it that the temperature will vary? If, let's say, I consider this to be the depth, if I consider this to be unit of temperature, let's have a marking here. Let's suppose 25 degrees Celsius, 24 degrees Celsius, all the way to 3 degrees Celsius. Now, closer to the surface, let's suppose this is the what you consider as the surface, the zero. Now, closer to the surface, the temperature will be around the region of 24 to 25 degrees Celsius. The temperature will be somewhere around 24 to 25 degrees Celsius. And as you start going lower, the intensity of sunlight will start reducing. And when the intensity reduces, its ability to heat up will also reduce. So as you start going deeper, let me represent it by a different color, the temperature begins to reduce, right? Because the intensity reduces. Eventually, in this portion, here you will observe that is a transition between the photic and the aphotic zone. Here you will observe that as you move to the depth, the because the sunlight is decreasing very rapidly now. You are already at a depth of 400, 500 meters. Sunlight is reducing very rapidly. 1 meter that you go, lot less amount of sunlight. 1 meter more deep you go, lot less availability of sunlight. So the temperature will also end up decreasing quite drastically. And then eventually, when you reach the aphotic zone where no sunlight is available, where no sunlight has been available for a very long period of time, so in that case, the temperature largely ends up remaining consistent. So, in the zone where the sunlight starts to reduce to being completely absent, that is a zone where the transition in temperature is very huge. The decline in temperature is very immense. So, this zone of transition, this is what is also regarded as a thermocline. Okay, where the temperature has reduced quite drastically because of reducing intensity of the solar rays, eventually leading to the aphotic zone. So here that is the thermocline, a region where there is a rapid decline of temperature. That is what we refer to as thermocline. It is also something which extends from 100 to 400 meters below the sea level, can extend up till 500 or 600 meters, but not beyond that. Overall, you will observe that as soon as you enter into the region of aphotic zone, there is largely a consistent temperature. What are the reasons for that? Why is it that you will find consistent temperature at the bottom of the ocean? You will find consistency in general, both in the case of temperature also, and when we study salinity, there also you'll find consistency at the bottom of the ocean. Ocean bottom has not been disturbed for a very, very long period of time. For millions and millions of years, the temperatures, the salt content present at the ocean bottom have largely remained the same. That is why it is always said that if we are able to study the species living in the ocean bottom, That will not only give us immense amount of idea into the process of evolution, that how evolution has happened. We will also get an idea about what life used to be millions of years ago, because many of the species that you find in the ocean bottom, they have a very unique structure in terms of the eyes, the head of the fishes, etc. The body is transparent in many of the cases. So that is why ocean bottom is something which is largely consistent. Now, why is it that ocean bottom, here you will observe temperature is largely around 4 degrees Celsius. 3 to 4 degrees Celsius is the temperature that you experience. So, temperature at ocean bottom is largely consistent. And why is that? Why is it that the temperature at the ocean bottom is largely consistent around 4 degrees Celsius? So there are a couple of reasons for this. So the first thing before and the reason, yes, Dipesh, perfect. So basically, here, before talking about the first reason, you have to understand the very basics. That something that you would have covered in your class 6th or 7th standard science. So basically, we do know the property of water, the density of water. Density of water is maximum when? Density of water is maximum at 4 degrees Celsius. If water cools down beyond 4 degrees Celsius, it starts forming ice particles. And for that, it needs to expand ever so slightly. Now, having said that, keep that on the side for a brief moment. We will use it after some time. Now, at the ocean bottom, the pressure is so very high that it is something which we cannot even imagine right now. That is why you would see that all the larger submarines, the mighty submarines constructed by the various different navies of the world, I hope you are aware that they have a service ceiling. That is, they cannot go beyond a depth of 400, 500 meters. And the best of the submarines, they can go to a depth maybe close to around 700, 800 meters. That is why for going to the ocean bottom, you do need to devise a new vessel altogether, a separate kind of a chamber altogether, right? That is what India is doing under the Samudrayan mission. Now, the pressure at the bottom is going to be very, very high, very high. So that is why any times when you have a submarine disaster, what happens? Submarine basically falls on the floor of the ocean. And when submarine falls on the floor of the ocean, the pressure crushes the submarine, almost like you have the empty soda cans that you have, the Coke and the Pepsi cans that you have, how we are able to crush it very easily. The pressure of the water also crushes the submarine just like that. So that pressure which is exerted, pressure also induces some amount of heat, right? Pressure will induce some amount of heat. So there is some heat which is produced at the bottom because of the pressure induced from the topmost layers. And that heat maintains the temperature around 3 to 4 degrees Celsius, does not allow the water to get frozen. So here, heat produced is due to the overlying pressure maintains the temperature. Okay, the heat produced due to the overlying pressure maintains the temperature roughly around that, and also density of water is the highest at 4 degrees Celsius. Cooling beyond that, what it does is leads to expansion of water. Now think about it for a brief moment and apply the logic here. You have that much pressure being exerted from the top. So, when that much pressure is being exerted, any material, it will find it very difficult to expand, if not impossible. It will find it almost impossible to expand, isn't it? Because there is so much pressure acting from the above. Now, that is why, if let's suppose water reaches 2 degrees Celsius, 1 degree Celsius, 0 degrees Celsius, it has to form ice. Now, ice is an expanded form of water. For that, the pressure needs to be reduced, but that cannot happen. So, these are the reasons why you will experience pressure or temperature at the ocean bottom to be largely consistent. Okay? So that is basically the variation in terms of temperature. You need to understand the variation in the vertical aspect and the variation in terms of latitudinal aspect. So here, what is it that we have studied in the portion of ocean temperature? We have studied that the temperature, first of all, the prime source is the sun, right? Now, sun will heat up the surface first. That is why generally the surface is the warmer layer. But as you go to the depth, as you go increasingly to the depth, what do you come across? You'll find that the intensity of the solar rays, they keep on reducing. So that is why the temperature decreases quite significantly. And that significant decrease or change in temperature, that is what we refer to as thermocline, right? That is the decrease or the decline in temperature. We have seen that at the bottom, the temperature is largely consistent around 3 to 4 degrees Celsius. And there are a couple of reasons for the same. First is the heat produced due to the overwhelming and high pressure exerted from top of the ocean. And second, water does not have the scope to expand. And if water gets cooled down beyond 4 degrees Celsius, it has to expand, right? So that is why temperature is maintained because of both of these factors in general. Okay. Now, horizontal distribution, we have talked about it, isn't it? So horizontal distribution, we have talked that what are the factors which contribute to horizontal or which are influential in horizontal distribution of temperature. We have the factors of latitude, unequal distribution of land and water, the prevailing winds, that is onshore and the offshore. We have the existence of or if the region is surrounded by landmass, then there will be variation in temperature. If let's say there is presence of ocean currents, then there will be variation in temperature. So all these are basically the horizontal factors. Okay. Cooling leads to compression. Okay. Samarjit, in the case of water, what do we have is that when we talk about the solid uh, aspect of water, that is ice, ice has got the crystal shape in the various particles, the molecules that you find in the ice, that has got a crystalline shape. Now, for the crystalline shape to form, it is not like any other, let's say, this solid pen or the solid, let's say, iron, etc., where all the particles are closely bound. So, here, in order to form that crystalline shape, that means the particles will need to have some spacing between them, which is not the case in the liquid state of water. So, water is a kind of a discrepancy, a kind of an exception or anomaly in that case, where it does not follow the normal or the general norms that you see. That is why you can experiment it at your own house itself if you have not tried it till now. High time in your life that you try these things. Do one thing: take any of the plastic jugs or jars or bowls, anything where you can freeze water. Now, fill water up to a particular level, allow it to freeze. Even in the case of the ice tray, you will observe that when the ice forms, there is an expansion in volume. So, ice is always an expansion in volume which is observed. Pavitra, onshore winds are basically the winds which come from sea to the land. Offshore winds are those winds which move from land to the sea. Okay? Due to western disturbance that India is facing now leads to lag in the movement of the ITCZ. Yes. It is not only the western disturbance, but in general, any kind of rainfall which is created, Ashwant, during the month of May, that will delay the formation of the low pressure. Right? If let's say May was very hot in many parts of the country, but northern part of the country did continue to receive a lot of rainfall, due to which increased amount of low pressure was not formed. Okay. There is no heat which is present in the aphotic zone. No. The source of heat is not there. The pressure generates the heat, the hydrothermal heat that is present, that is generated by the pressure itself. Okay. Warm water at the surface and cold water at the depth leads to foggy conditions. No. For the formation of a fog, you need temperature interchange at the surface, not the depth and the surface. Right now, we are considering the depth and the surface. Have some patience. I'll come to the portion of Labrador and Gulf Stream. You will understand it better. Okay? Right. So now we come to the portion of oceanic salinity. So, when we talk about oceanic salinity, that means expansion of water is not possible at great depths. That's why temperature remains same. One of the factors. The other factor is the heat generated due to immense pressure. I have written both these factors here, guys. Both these factors are responsible for the maintenance of temperature, similar temperature. Okay. The pressure is going to generate some heat. Now, oceanic salinity. Salinity is what? Salinity is basically the amount of salt contained in the ocean water. That is salinity. For anything, for any solution, if you have to talk about salinity, it basically will end up measuring the salt content in one particular sample size of that solution. For example, let's say I consider the oceanic water. In general, all those of you who have been to a coastal area or who have been to a sea before, you would have experienced that when you get into the water, sometimes the water which gets inside your mouth, you feel a very salty taste associated, a very saline and a salty taste, like the common salt that we have. So that is where we come to an understanding, a basic understanding, that oceanic water is salty, it is saline. Whereas the river water that you receive, the stream waters, they are fresh water. Now, how do you end up measuring salinity? So, salinity is basically measured by taking the weight of the salt in, let's say, 1 kg of water. Okay. Let's say I consider 1 kg of water. Now, in that 1 kg of water, what is the salt content in that case? That is something which measures the salinity. Now, what are the salts which are present? So, you have various different types of salts, from the common table salt that we consume, that is sodium chloride, to magnesium chloride, potassium chloride, calcium sulfate, potassium sulfate. All of these are present in varying proportions. Overall, if you take it on an average, you will find that NaCl or sodium chloride, what we consider as a common salt, that is one of the dominant salts present in the oceanic water. Now here, in 1 kg of water, when you calculate the amount of salt present, it comes out in the range of around 20 to 30 or 35 or 38 grams in general. Varies with various areas. So, the salinity is expressed in the quantity of salt per kg of water. So in this case, let's assume we consider 30 grams of salt is present. So that will mean 30 grams per 1000 grams of water. Now, whenever you use the term per thousand, right, parts per thousand, so it is 30 parts per thousand. In this case, 30 grams per 1000 grams of water. So that is why salinity is also something which is expressed in parts per thousand. Okay. Now this parts per thousand overall means you take a unit as 1 kg at the denominator. 1 kg of water at the denominator. That is why you express parts per thousand. And this is expressed by the unit or the symbol like this. Average oceanic salinity across the globe. Average salinity is 35 parts per thousand. Okay. However, you have certain areas where the salinity can come down to zero. You have certain areas where, for example, if you consider one of the most saline water across the world, where is it present? Which is the most saline water across the world? It is Lake Van in Turkey. Lake Van in Turkey, I understand that all of us have from our childhood days, we are fed with the data Dead Sea, Dead Sea, Dead Sea is the most saline water, but it is absolutely incorrect. You have few of the areas which are much more saline than the Dead Sea. It is the Dead Sea which has become very famous, but Lake Van in Turkey is basically one of the most saline regions in the oceanic water. So in that case, you can have the salinity as much as 330 parts per thousand. That means in Lake Van, in 1 kg of water, you have 330 grams of salt which is present. So you can imagine the salts which are present. Now, where do the salts come from? What are these salts? So, as I told you, these salts consist of various different uh, types of constituents, from the chloride ions to the sodium ions to calcium, sulfate, potassium, magnesium, carbonate. Everything ends up creating these salts. So, how are they supplied? So, underwater volcanic eruption, whenever it happens, it ends up supplying a lot of salts. For example, when you consider the oceanic area, let's suppose, when you consider the oceanic area, so in this ocean, right? So here, if suppose this is the land, so at the region of land and ocean interface, materials will start dissolving and they will add to the salt or the saline content of the ocean. It is one of these methods by which a lot of sodium has been supplied. A lot of sodium has been supplied to the oceanic water. Also, you have various rivers and streams. These rivers and streams, they will also end up bringing some amount of salts into the ocean. You have various different biological processes carried out by the endless number of species which are present. They will also bring and add salt to the ocean. So these are the various factors which keep on adding salts. Let us take a look at that. So the total content of dissolved salt in the seawater, that is called salinity. It is calculated as the amount of salt in grams dissolved in seawater of 1000 grams or 1 kg. Okay? And that is what is expressed as parts per thousand. Parts per thousand. Why? Because the sample, as the sample is of 1000 grams of water. Now, seawater you will find has got various different ions, and these ions will end up interacting with each other and they will form the various different salts. Now, this image basically gives you an idea about the sources of addition of salt in the oceanic water. Okay, so for example, when you have volcanic eruption brings about significant amount of calcium, potassium into the salt, into the water. Then when we talk about the river discharge, when we talk about the sediments and the dissolution of the rocks nearby, you have carbonate, calcium, sulfate, sodium, all of these are added, right? So that is how basically you have the addition of the salt. Now, if you apply logic here, that takes you to another corner and another kind of dilemma. And that is that if salts keep on getting added up, oceans have been created much earlier than the landmass. Oceans have been in existence for billions of years. So if the salt content keeps on getting added up, how is it that the average salinity of the oceanic water is still considered to be only around 35 parts per thousand? The salinity should be very, very high. That is because on a periodic basis, as the salt is getting created, that salt is getting dissipated as well. Over a period of time, let's suppose you have various different salts here. Over a period of time, few of them can get together. And when they get together, they will form a larger particle slowly and steadily. And that is when they will eventually end up sinking, right? So you will find that various different larger particles are created as the salts they start getting together. Much of the salt or some amount of the salt is also consumed in the biological process. For example, you will study in the portion of environment and ecology again that when we talk about the corals or the coral reefs, now the corals, they have a very unique ability to synthesize calcium carbonate from around them and then manufacture that calcium carbonate reef. Now, that will also consume the salts. Similarly, if you consider all the shell bearing animals, the shells that they build around them, now those shells, they are also built of calcium carbonate taken from the water of around them. So biological processes, they also will consume some amount of salt. Some amount of salt, as I have told you, will get deposited. Some consumed by the biological processes. Some salt will also get carried into the atmosphere. How? When we have the ocean, how is it that the salt will get carried to the atmosphere? It is by what we refer to as a sea spray. So, what is a sea spray? When I talk about sea spray, what is a sea spray here? So, let's suppose I have the water in this region, the oceanic water, and then here I have land. Let's say a rugged and a hilly part of land. Now, in this water, periodically, you will find that the waves will develop, isn't it? Waves will develop overall, and the waves will then end up crashing. Now, when the waves develop over here and they crash over this particular rock, what happens? It will release a lot of droplets, right? If ever, this is something that you find in larger proportion, larger majority in the case of the Western Ghats. So across the western coastline, particularly the Konkan coastline, that is why in many of the cases the beaches are regarded as very dangerous. But across the Konkan coastline, if you go, you'll find that when these waves they crash, there is a lot of spray which is emitted. That spray that you see, that is what is the sea spray. Now this sea spray will consist of very fine particles of salt that it can, and eventually you might have the winds moving over a region. The winds will carry that sea spray further up. In many of the coastal areas, the salt that the sea spray has, that eventually reaches the upper levels of atmosphere. And that salt particle eventually, that provides a platform for condensation. So that is how sometimes even sea spray can be helpful in formation of clouds, because these salt content, when they go up higher up into the atmosphere, these salt particles they can serve as hygroscopic nuclei. The same role played by dust particles in the case of atmosphere, the same role can be played by the salt present in the sea spray as well. Okay, so that is how you have the formation, the dissolution, and the maintenance of the salts in general. So the supply of salt, the river will carry some amount of salt present. There will be some amount of dissolution from the nearby rocks, volcanic eruption, mid-oceanic ridges. All of them will keep on supplying salt into the oceanic water, into the oceanic region in general. Okay, so that is about the aspect of salts in general. Now, how biological processes help in consuming salt? For example, take the case of shell-bearing animals. Take the case of corals. They will consume the salt around them, and that is how they are able to maintain that large reef structures. The coral reefs are made up of what? Calcium carbonate, which is a salt. So calcium and carbonate ions which are present in the water around them, they assimilate them and then they use that. So once you carry out that process, aren't you reducing the amount of salt present in the ocean already? So that is the case how the salt is consumed by the biological process. Okay. Now, after this, these are the various salts which are present. Sea spray I am not getting. Okay. Lakshmi, can you, where benthos species are found? Lakshmi, I've already answered this question in the same session twice. Please kindly, when you ask a question, kindly pay significant attention. It should not be that the same question is being answered again and again and again. I've already told you, ocean, the benthos and the benthic species are to be found at the ocean bottom where the light is not available. That is the species that is referred to as the benthic zone, and that is where the species which are found are referred to as benthos. And these benthos, they are specialized in handling very high amount of pressure and living in perpetual darkness. Okay, now coming to the sea spray. Okay, sea spray you were not getting. See, what is sea spray? What is a spray? Spray basically refers to whenever, okay, you would have observed, let us consider this in very simple terms. When you consider the sea water in the coastal area, when the sea water hits the coastline in the form of the waves, have you observed the emission of lot of small sprays? I hope we have observed that. All of you, those who have not understood, have you observed that when the, let's say, ocean water, when it hits the rocks, what happens? It hits the rocks, there is a large splash which is created, isn't it? and then the water goes back. Now that large splash which is created, many of the droplets, they are very, very small. Few of the droplets are larger, few of the droplets are very, very small. Now those smaller droplets, that is what is referred to as a spray. When you have a, let's say, a deodorant or anything, so that there also you spray it out, isn't it? You spray it out, what happens? You have very fine particles and droplets which are emitted, isn't it? So similar is the case in the form of sea spray. So that sea spray basically, it also carries salt, because each and every droplet of seawater will have salt. It is not as if the salt is left behind and this water will be free of salt. No, each and every droplet of seawater will have salt. So when that crashes and that spray is created, that means the salt is also carried away, and then carried away by the winds, that salt is taken into atmosphere. So that is the case of sea spray. Okay. Now, after this, these are the salts which are present in various different proportions. Here you will observe that significant portion is dominated by the sodium chloride. Sodium chloride ends up contributing around 78% of the total salt which is present, and overall then followed by magnesium chloride, magnesium sulfate, calcium sulfate. So the first four again in this case needs to be looked at, needs to be understood. Okay, sodium chloride, magnesium sulfate, and calcium sulfate. So that is basically the proportion. In general, on an average, you have 35 parts per thousand or 35 grams per kg of oceanic water as salt. Now, there are various factors which contribute to the variation in terms of the salinity factors. That salinity is not consistent across. You have various events which will end up varying the salinity. So let us understand how is it and why is it that salt content varies when you go from one part of the planet to the other part of the planet. So we will understand that with the very basic aspect of when we consider variation in salinity. In salinity due to addition or will consider the factor of addition or removal of salt and water. How maintenance of salinity is carried out, because if you have salt which is created substantially and there is no removal, for example, then over a period of time, what will happen? The oceanic water will experience a lot of buildup of salt, isn't it? Periodic removal of salt also happens. You have dissipation of salt which happens. So salt dissipates by what methods? It deposits itself at the ocean bottom. Sometimes you will find that it in itself disintegrates, but other than that, you have the salt which is removed by sea spray. You have also got the salt which is consumed by the biological processes. So the salt is removed. So the salt is removed, the salt is added. Isn't that a maintenance of salinity which is maintained? I hope that is understood. Now, concentrate here and listen to this aspect carefully. Otherwise, again, you will be chasing this concept for I don't know how long. So, what is it that ends up influencing the variation in salinity? You have factors such as evaporation, precipitation, the melting of ice, the freezing of water in certain areas, mixing of groundwater, river water entering into the ocean. All of these will end up influencing the salinity. Now, here, How is it so and why is it so? So we'll understand that with the basic aspect of considering a water sample. Let's suppose in a very simple logical aspect, think about it. Let's assume this is the water sample. And here you have the water molecules which are present. Let's assume water molecules are present. Now, here water molecules are present. In between these water molecules, wherever the scope is available, you will have salt ions which are present, the salt which is present. Now, when you have the condition of, let's say, you experience the condition of rainfall. Now, whenever rainfall happens, it brings some amount of dust particles along with it. But if you consider a larger scale, a larger volume, rainfall brings about a net addition of water, or does rainfall bring about a net addition of particles in general? What do you think? An oceanic water or an oceanic area which receives rainfall, will it have only the net addition of salts or particles, or will it have the net addition of water? Good. You will have the net addition of water in that case. Some amount of particles will also be added, but in majority, water will be added, isn't it? So, in that case, now what do you have? After rainfall has occurred significantly, you will observe that as compared to the earlier scenario, the particles of water have indicated a marked increase, and the salts, they are present as they were. Now, as compared to the earlier image, this one, as compared to A, now the proportionality of salt overall or salinity factor, has it increased or has it decreased with the onset of rainfall? What do you think? In this case, the proportionality of the salt, as almost all of you have given the correct answer, proportionality of the salt in per unit volume or kg of water that you will observe here has basically decreased, because there has been addition of water. So salt content, the proportion of salt has reduced now because more water has been added. So salinity reduces. Salinity reduces with addition of water. Whenever you have addition of water, salinity will reduce. And what are the factors which will contribute to a scenario very similar to addition of water? So here you will have factors such as, let's suppose, rainfall or precipitation in general. Then you will also have melting of ice, river water, and then you also have groundwater. So all these will lead to the net addition of water. And whenever there is a net addition of water, salinity ends up reducing. Salinity decreases in general. Now, what if we consider the another scenario? Let's suppose here you have the water particles. You have the water particles, right? And in between them, you have the salt ions which are present. Now, in this situation, let's suppose you have the event of evaporation. Which happens. Now, evaporation which happens overall, what do you think? Whenever evaporation happens, you will observe that always the dissolved material gets left behind. Only the water evaporates, the dissolved material gets left behind, isn't it? If you have ever experienced this, observe that whenever, let's say, you have a salt solution, you keep it out into the sun. When you have evaporation which happens, the salt content will be left behind. So here, when evaporation happens, you will observe that the water molecules are now comparatively lesser because the water molecules have been evaporated and the salt has been left behind. So, as compared to earlier, you would basically experience what? You would experience that the salt content or the salinity is higher, increases whenever there is removal of water. Due to removal of water. Now, what are the factors which can bring about removal of water? So, one of the factor is evaporation. The second factor is, significant factor is freezing of water. Freezing into ice. So, here we might have the logical argument, but when water freezes, you have some salt particles which will also freeze. Fair enough. But when you have freezing, so in larger quantities, what freezes up? Water freezes up. So in a region, let's say where ice has been formed, a large iceberg is created. Why does that happen? That happens as the surrounding water that starts to freeze up. So it is the surrounding water which is removed. So obviously, the water supply or the water available will be lessened. So that is how the salinity increases in these cases. So overall, you will observe that surface water salinity where evaporation is more, wherever evaporation is more, means salinity will also be higher. Okay? Wherever precipitation or rainfall is more, means what? More precipitation or more rainfall means lesser salinity. Lesser rainfall means greater salinity. Isn't it? Then after that, fresh flow of river water. River water, wherever you have the river water exiting into the ocean, salinity is lower because river water is considered to be fresh water. And then freezing and thawing. Thawing here indicates melting of glacier. So you have freezing and melting of glacier. So freezing increases salinity, and thawing decreases salinity. Okay, so there is a compilation here. So anything which removes water from the system the salt is left behind, so that will lead to an increase in salinity. For example, freezing of seawater, from all around, water will be consumed to form the ice, whereas some amount of salt will also get frozen up. But please understand and look at the larger picture. All those of you who have the same set of doubts, and I'll tell you, the doubts prevail in the same range and in the same pattern. The doubts that many of you will have right now is, river water brings in some salt. Why are we saying that it only brings about addition of water? Groundwater has presence of minerals. Why are we saying it reduces salinity? Freezing of water, when it will happen, it will consume salts. Why are we saying that it increases salinity? So always understand the very simple aspect that whichever process is being carried out, whether in total, in larger area, whether it means removal of water or whether it results in addition of water, as simple as that. So when, let's say, from a particular oceanic area, you have a large iceberg which is formed, a large ice which is created. Now if I ask you, this consists of ice or water in majority or salt in majority? Obviously water in majority. Water has formed that ice. Salt has not formed that ice. You will have water in majority. Now that water in majority, if it has formed the ice, that means in the surrounding region, now there is lesser water. That is the reason why during ice ages, we experience the water level across the globe. Water level reduces during the ice age. And then again during the phase of warming, what happens? Water level again rises up, isn't it? So even if you have a doubt, let's say that rainwater, you are saying rainwater will reduce salinity, precipitation will reduce salinity. But I have seen that rainwater has got some particles included in it. But overall, if you consider on a larger scenario, that rainwater will be dominated by what? It will be dominated by water and very little amount of particles here and there. So there will be net addition of water in general. Similar is the case with river runoff also. It might add few grams of salt, but for those few grams of salt, it would be adding kgs of water altogether. So again, you have net addition of water. Same is the case wherever you have the groundwater flow to the ocean. So all these factors, melting of ice, precipitation of rain or snow, etc., everything, they will lead to addition of water. And addition of water means a decrease in salinity. This should lead to removal of water. And that leads to increase in salinity in general. Okay? Then, sir, in ice age, the volume should increase. Hmm. In ice age, why the volume should increase, Pinto? Because ice has got a greater volume than water. Okay. By ice age, we don't mean that all the water in all the ocean is frozen. Please understand, ice age does not mean, as you see in the animations, that everything is frozen. Wherever someone was walking in that posture itself, that individual is frozen. No. When you have the ice age, during the ice age, the polar region and the higher latitude, they get frozen significantly. So the water in those areas in the higher latitude, there significant amount of freezing happens. But there also, in majority of the regions, you will still find that at the bottommost portion of the ocean, still you have liquid water which is present. So ice age does not mean that Atlantic will now be a solid because everything is frozen. No. Only the northern latitudes and the extreme southern latitudes, there you will have increased formation of glaciers and ice caps in general. Okay. How freezing leads to decrease in salinity? Freezing basically will remove water because it is the water which forms that ice, hence it will lead to decrease in salinity. So this is the basic latitudinal variation that you will observe in terms of salinity conditions, aided due to precipitation and evaporation, aided due to the rainfall and the evaporation condition. How? So here if you observe in this case, observe around the region of equator here, around the region of equator, we end up receiving very high amount of rainfall. So the rainfall received is very high. The rainfall received is very, very high, right? Whereas evaporation is not so very high around equator. So overall, if the rainfall is more, salinity is going to be lesser, isn't it? Then, when you come to the subtropics, in this region, rainfall is very less. And why is that? This is the region of the subtropical high pressure. This is the region of subtropical high pressure. So subtropical high pressure zone means almost negligible rainfall. But temperature is high. So here you will have evaporation, right? Further augmented by the presence of the trade winds and the westerlies in this region. So that is why here it is in this area around the tropics that the salinity is going to be maximum. That is why salinity is maximum at the tropics. Okay. Salinity you will come across as maximum at the tropics. And then slowly and steadily, it keeps on reducing as we move towards the poles. The salinity keeps on reducing in general. But there is a lot of variation around the region of the poles, depending upon whether materials are melting, whether the materials are freezing. So there are various other factors also involved in determining the salinity across the polar areas. So this is basically only the influence of evaporation and precipitation curve, which helps us understand why salinity is maximum around the tropics. Now here also, if I ask you that as compared to north and the southern hemisphere, where do you think salinity will be greater? In the northern hemisphere tropics or in the southern hemisphere tropics? Where do you think in comparison salinity will be greater? Very good. Northern. And why in the tropics of northern hemisphere? Because in the tropics of northern hemisphere you will find the greater presence of land, and greater presence of land means greater heating, means greater evaporation. Greater evaporation means higher salinity. That is why higher salinity is something to be found in the tropics uh, of the northern hemisphere. Now the horizontal distribution of salinity, we'll take a look at it. We'll take a break first. So we take a break for 10 minutes and then we'll be back. Okay, should I keep it at the last slide? Okay, I'll keep it at the last slide. Molecules, particles are made up of molecules. Molecules basically is the individual component which make up any state of matter, molecules constituted by atoms. There's also rain near equator and tropics. No, there is not much rain in the tropics. Tropics are very, very dry. Across the world, the tropics are very, very dry. Other than India, India is an anomaly because of the presence of Himalayas. Otherwise, take a look at the tropics across the world. Take a look at our western side. If you take a look at the western side, be it Pakistan, be it Iran, be it Iraq, be it Syria, most of them are very, very dry. A red line depicts, it is given here, my dear friend. Red line depicts precipitation. It is given here what is red line, what is blue line. Kindly take a look at that. Okay. At the subtropics, there will be high pressure, isn't it? We have seen that in the atmospheric circulation. Subtropics will have high pressure. So that is why you will find that high pressure means absolutely negligible rainfall. If water vapor condenses on dust particles, then why rainwater is clean? Who told you rainwater is very clean? That is a kind of a misconception. And that rainwater is the cleanest of them all. In many parts of the country, we receive acid rain, right? Where you have the rainwater being able to dissolve nitric acid and sulfuric acid created as a result of pollution. So the next time that you see on the videos or on the media channels, the various influencers having a sip of the rainwater, wish them good luck, because rainwater is never going to be very, very clean. Okay. So let's take a break now and we'll be back in 10 minutes. A confirmation about the audio, please. If the audio is clear and available, kindly confirm the same. Thank you. Pavitra, you said your question is, you said that equatorial region has more evaporation, which also indicates more rainfall. So then we more land mass in northern hemisphere than southern hemisphere, which indicates to have greater heat from land and greater evaporation, that is greater rainfall in northern hemisphere. No. So here, please understand, Pavitra, evaporation does not mean it will lead to rainfall. Evaporation does not always lead to a causation of a rainfall. Evaporation, so for example, think about it. Let me paint a scenario in front of you. If I have, let's suppose, the ocean water in this region. And in fact, rather than the ocean water, think about the very basic aspect. When you wash your clothes in general and you put it out to dry, now when is it that the clothes will dry quicker? When you have the movement of winds or when you don't have any movement of winds whatsoever? Always you will find that whenever you have wind movement, the clothes will dry much quicker, isn't it? Why is that? That is because whatever is evaporating, that is carried by the wind. So that means more evaporation will be carried out in that region because the air becomes unsaturated again. So that is why evaporation does not necessarily mean that that particular region in itself will receive high amount of rainfall. If you consider the subtropical high pressure belt region, that is the horse latitude. So in that subtropical high pressure belt, you have absolutely negligible amount of rainfall. Rainfall is absolutely almost absent. And why is that? Because of the high pressure. But the temperature is high. So the evaporation will continue to happen. So in the northern hemisphere, if you consider the Red Sea, the Persian Gulf, the Gulf of Aden, any of those areas, lot of evaporation happens, but not so much amount of precipitation. Hence the salinity is much more higher. Is that understood? How abyssal plain is impacted from submarine canyon? Almost no impact at all. If water creates that much pressure, then why not the land under the sea or the ocean go down? Where will it go down? You mean that it gets compressed significantly, but if there you would have had a situation that underneath that oceanic landmass or the underneath the oceanic crust, if it would have been a vacant space, maybe it would have subsided. But underneath also you have the mantle. So there is compression due to which the oceanic crust becomes much more denser over a period of time. Okay. Precipitation does not remove salt. Shalu, precipitation, what it does is it adds more water. So the proportionality of salt over a period of time reduces. That is the impact of precipitation. Okay. Hydrothermal activities at mid-oceanic ridges can add more salts in water. Vedshri, what it does is whenever you have, let's say, the volcanic events at the region of mid-oceanic ridges, we have active volcanism. So in those areas, those volcanic materials, those molten materials, when they come out, few of them will dissipate in the form of salts. So that is how it will increase the salinity. Why we find a hike in salinity in doldrums? The salinity is less at doldrums. The precipitation is very high due to convection rainfall. Yes, Rahul, that is correct. What is the difference between precipitation and rainfall? Okay, rainfall is a kind of precipitation. Snowfall, rainfall, any of these that you consider, it is precipitation overall. Okay. Pinto, I would suggest that revision of the content that you have understood is as important as it is. So here, when you have when you have, let's say, covered any particular video, always, or attended any session, it is important to revise it within a week. So you can revise it whether by the looking at the PPTs itself, or you can take a look at the tablet videos. I'll give you the exact detailed aspect of how to go about the revision in the next portion, or in the next week when we are about to conclude the entire portion. Okay. Um, Shalu, what you are talking about means, in the case of precipitation or rainfall, here observe what does the PPT tell you. Take a look at it carefully. Less precipitation means more salinity. So, what can this be inferred as? It can be inferred as more precipitation means lesser salinity, isn't it? So, those regions where you have less rainfall, there's less addition of water, hence, you have less salinity. Okay. uh Elias, in the case, let's suppose you don't have a tablet, don't worry. Revise it from the recorded sessions or the annotations of the PPT along with the additional reading material. More than sufficient. Sea sprays are also visible with the naked eyes. See, Elias, one thing that you have to be mindful of, and that is the thing which is very important for the entire preparation of civil services. That is how civil services is different from your CAT exam and other exams that you appear. In the other exams, the completion of syllabus is the major part. After that, your work is done. Here, unless and until you don't revise it within 20-25 days, regardless of whatever genius you are, regardless of whatever your DNA is constituted of, maybe you will have the genes of um, Isaac Newton and Albert Einstein, both of them working simultaneously. Still, you have so many different details present here in all the subjects that you will end up getting confused, invariably so. So if you want to keep a track and a control and a grasp over your preparation, follow the ideal, the golden three stages of revision. That is the golden rule for revision. First, anything that you study has to be revised within the first 7 days. The second phase of revision for that material has to be carried out within 15 days, and the third phase of that revision should be completed within 30 days since you first studied it. Only then will you be able to retain it. Otherwise, think about it. What you are studying right now, if you have that expectation from your mind that you will be able to retain it till the prelims and the mains next year, either you are a kind of a born genius or a prodigy that the world is very fortunate to have discovered, and or the other scenario will be that you will be completely awashed with so much of data by next year that you might end up contemplating the option that, okay, I will give the exam next year. So you will never be able to recall it, what you have studied today, next year in May or June. That will never happen. Okay. So that is why periodic revision is very important. Tablet video of geography is covered by you only? Yes, my dear friend. So if you take a look at it, it has been covered by me only. And while covering that, I have ensured that we cover each and every portion right from the very basics. For example, in climatology, we have included a separate module only for basics. For those of us who have little clue about evaporation, latent heat, freezing, melting, all those aspects. So we have covered a different unit. In that, we have covered the speed of the wind, that what is a storm, what is a wind, what is a breeze, what is a gale. So the Beaufort scale, which is used for delineation of the wind. So it has been covered quite extensively. Okay. Sachin, but in my tablet is other faculty. Okay. In that case, kindly take a look whether you have the updated memory card or not, or you can ask for the updated memory card. You will have those lectures available. Yes, essay videos are covered by me in the tablet as of now. Yes. Chinmay, will you take ecology classes? Depending upon the availability of time and the schedule, I will try to take it, but it depends on the schedule. So kindly inquire before your in ecology classes, and I will let you know. Okay. Nisarga, delayed onset of monsoon and the low pressure form near Arabian Sea and it moves towards Oman. Delayed onset of monsoon and the low pressure form near Arabian Sea and if it moves towards Oman. Will it decrease the monsoonal effect in India? Obviously, yes. But what eventually ends up happening is that over the next few days, over the next 15 days, ideally you would experience, as per the prediction as it goes now, over the next 10 to 15 days, northern part of the country will get much more uh, hotter. And that will lead to the formation of the low pressure across the northern part of the country. And that will bring the ITCZ. ITCZ will also exist over the Arabian Peninsula. But please understand the trade winds, when they cross the equator, they will deviate to the right. So naturally, they will be coming rather than moving over towards the region of Oman and so on. They will naturally have a deviation and bend towards the Indian subcontinent. And Kishan, today's essay lecture will be recorded or live. It will be live. 12 to 3, it will be live. And then from Friday class onwards, why there is economic PPT and ARMs are present in geography session. Satyajit, if that is the case, humble apologies for that, first of all. And if you face these kinds of issues, immediately get in touch. You have my mail ID. I'll give you the mail ID. I want you to be a bit more proactive. Send a screenshot of that, whatever you have come across, and we'll resolve it immediately. Okay? Send a mail over to me and with the screenshot, and I will get it resolved. That is a kind of a assurance that I can provide to you. Okay? Anshu, fair enough. In that case, if it is by the other person, fair enough. Overall, if the gist is covered, more than sufficient. Right? So that is, I hope the queries are resolved. The last question I'll take is yes, Siddharth, I'll be taking the class today. Um, the current affairs part of geography, you can cover it. Newspaper reading is the only option which is present and the viable option. So, newspaper, if you go through, it will be sufficient. Okay. And Tejinder, you have to get some time out for the newspaper reading, regardless of whether you are working professional or not. Download an app on your phone. Start with following the current affairs. Slowly and steadily, you will have the habit or the knack of reading, which is important. And on your weekends, when you can extract more time, use that for your optional preparation. If you don't have newspaper, that is why I'm telling you, download an app, read the news articles on the phone, but either the Hindu or the Indian Express, you have to read it. Get into the touch of reading that. Okay? Right? Uh, I didn't receive my geography books till now. So there has been a kind of a delay for the materials. And I have another one of you asking the query about that as well. It is something which is being worked upon. And we have a lot of people working on that. Don't worry, we'll resolve it as soon as possible. Okay. So now we continue with the portion of horizontal distribution of salinity. Should I make notes from newspapers? If you have time, my dear friend, fair enough. You can make micro notes from newspapers, the important points. If you don't have that much time as of now, don't bother. Just take a look at the newspaper reading on a daily basis. Look at the analysis, maybe at a faster speed, 1.75, 1.5, 1.75, depending upon your comfort level. And monthly magazines that you get at the end of the month, revise that multiple times. Each monthly magazine for the past 15 months should be revised at least 5 times before you enter the prelims exam hall. Look at the trend of questions being asked in prelims. Last year, prelims asked you questions about Miyawaki method and bio-rock, which were present in news headlines for the past 2 years. This year, UPSC has asked you about Wolbachia in science and tech. Again, something which was prevalent in news story for the past 15 months. So get in touch, revise it as many times as possible. You will be in a sweet spot. Okay. Newspaper app, any of them, the aspect of the Hindu or the Indian Express, and newspaper reading is a must, regardless of how you reframe the question, how you try to trick me into saying that just read this much more than sufficient. I won't fall for that trap. Newspaper reading is a must. Now we come to the horizontal distribution of salinity, which basically means how salinity varies from one region to another, how the salinity in various different waters in seas, they end up indicating a variation. So on an average, the oceanic area on an average, they indicate a salinity of 35 parts per thousand. Okay, so that is the salinity on an average. Now, the salinity for normal open ocean ranges between 33 to 37 parts per thousand. In certain areas like the Red Sea, salinity can be around 41 parts per thousand, whereas in estuaries around the region of the Arctic, salinity can vary from 0 to 35, depending upon whether melting is happening, freezing is happening, etc. How many of us are not aware what do we mean by estuaries? Any of us who is not aware about estuary? Okay, fair enough. So when we talk about an estuary, it is first of all very different from a delta. Delta is where as the river enters into the sea, it starts depositing materials in that region, forms a delta. Estuary is slightly different, where you will observe, if let's suppose this is the land area, this is where, let's suppose this is the land, this is the land, this is where the river is moving, this is where you have the sea. So, while the river water, which is the fresh water, enters into the sea, this is an area where some parts of seawater also start moving inwards. So, this entire aspect, this entire region, that is a zone of transition between fresh water and saline water. This is what is referred to as an estuary. Now, apply your normal sense of logic here. If I ask you point 1, point 2, and point 3, salinity will be lowest at which of these points? 1, 2, or 3? What do you think? Lowest salinity. Lowest salinity will be observed at point 1, where you have the river water, which is dominant. Salinity will be highest at point 3, where the seawater is dominant. So that is why in the region of estuaries, you will find that as you move closer to the sea, the salinity tends to increase, and there's a great variation of salinity from one region to another. And the species living here, that is why you will find in estuaries you have a significant variation in terms of salinity conditions, and the species also are very significantly varied. Estuaries are the regions where you will find a lot of species in presence, species who are tolerable or tolerant to fresh water, species who are tolerant to saline water. A lot of various species are to be found. Again, something that you will study in greater detail whenever you cover the portion of environment and ecology. You will be introduced to the term of ecotone, and why that is very important for protection and conservation of biodiversity. Estuaries can be very, very large. Estuaries in certain areas can be many kilometers in extent, right? So estuaries can be very large. Okay. Example for estuary: when river Narmada meets Arabian Sea rather than a delta, it forms an estuary. When river Tapi meets the Arabian Sea, it also forms an estuary. When we consider, let's say, the regions around eastern coast, there also you have formation of estuaries. So estuaries are basically created as a result of that. Now, here is another image I want you to observe carefully. And that is the variation in terms of oceanic salinity experienced in different areas. Now, here, if you experience or if you observe for certain facts, observe how salinity is higher in the tropics, in the northern latitudes. Why? It is a subtropical region, greater evaporation, almost negligible or nil amount of precipitation. Hence, salinity is very high. Then, observe here the Mediterranean. Salinity is still very high. Why? Closely surrounded by land mass, much greater evaporation. Hence, you have increased salinity. Observe the region of the Red Sea. Very high level of salinity in general. Okay? Now, then after that, observe this area to the west coast of Africa. You will observe that the salinity is low there. Why do you think? Or what do you think is the reason why salinity is suddenly very low in that region? Very good, Pooja. Beautiful. Shalu, correct. Deepesh, correct. Here you have the large river, that is River Congo. River Congo ends up entering into the region of Atlantic here, and fresh water or river water reduces salinity. Then observe this particular region, Bay of Bengal, and compare it to the region of Arabian Sea. Overall, in the region of Bay of Bengal, you have Brahmaputra, Ganga, Mahanadi, Krishna, Kaveri, Godavari, Penar, Iravadi, all the larger rivers. They will be draining into the region of Bay of Bengal. Whereas in the case of Arabian Sea, at max, if you consider the larger rivers, you will have the presence of what? You will have the presence of, let's say, the river Indus, Narmada, and Tapi. These are not very large. But here you have many large rivers, hence salinity is low, right? So Bay of Bengal, as compared to Arabian Sea, has got a low salinity. Are we comfortable with this? That why low salinity in Bay of Bengal? I hope no issues. Good. Now we will elevate the concept. So before that, in when we talk about hot and dry regions where evaporation is high, salinity sometimes reaches up till 70 parts per thousand. Maximum salinity generally observed in the tropics in the northern latitude. Now here, even when you consider the North Sea, this particular area, here also you will find salinity is high, which is unusual for very high latitudes. But salinity is high. Why? Because saline waters and warm waters are brought about by North Atlantic drift, and North Atlantic drift is an ocean current. Okay, so that is why you have certain variations in salinity. Now, we are going to talk about the salinity conditions of Arabian Sea and Bay of Bengal. We do know which has got more salinity. Arabian Sea has more salinity. Bay of Bengal has got greater amount of fresh water. Now, we are comfortable to up till this concept. Now let us develop the concept furthermore. Let us try to form a kind of an interlinkage. So here, if I ask you about the weight, weight of water sample. So I have a sample A, let's say, having 35 parts per thousand as the salinity. And I have a sample B with salinity of around, let's say, 25 parts per thousand. Now, which of these waters will be heavier? A or B? What do you think? Which will be heavier? Good. Sample A will be heavier because it has got greater amount of salt in it. Greater salt means greater amount of density. It will be heavier. Anything which is heavier, naturally or normally, what happens is that it starts to sink. And anything which is lighter will tend to float. The basic concept that we have basically experienced in our lives, anything which is heavier will sink, anything which is light will float. Now, using that concept, let us write that concept here. Higher salinity means greater density. Greater density means more weight. Okay? Lower salinity will float and higher salinity water will sink. Now, it is not only restricted to this. Here, the difference in terms of higher and lower salinity will also have an influence on heating and cooling. Let us understand how. So when we talk about the region of Bay of Bengal, Bay of Bengal has got large amount of fresh water present in it. Large amount of fresh water is consistently every minute of the day. Large amount of fresh water is being added by all the large rivers. Now that fresh water is going to be lighter. Now that fresh water being lighter means what? It is going to float on top because fresh water is lighter. It will float on top because it has lower density. Whereas the heavier water, that will tend to stay at the bottom. Over a period of time, this will mix together. It will form a kind of a homogeneous water, but by that time more fresh water will be added. So consistently you'll find what? That the water arranges itself in the form of various layers. Fresh water ends up forming a layer on top, and then the saline water forms a layer at the bottom. So this layered formation or the arrangement of water in the layers, that is what is also referred to as stratification, right? This is what is also referred to as stratification of water. Of water. Where the less saline water or the fresh water tends to float on top, and the denser water that tends to sink at the bottom. Now here, when you have the stratification which is observed, let's suppose you have the solar insolation. Now the heating by the sun in general, if let's say the water would have been very, very homogeneous. For example, in Arabian Sea, let's suppose water is homogeneous even up till a depth. So, solar insolation in that region would be distributed evenly. So the solar insolation would be distributed very evenly. Whereas when we talk about this particular area or this particular image, the solar insolation here would significantly get trapped. Some part will be dissipated, but significant portion will end up heating the topmost layers first. Isn't it? Because you have different layers indicating different density. So we do know that as light travels, light when it moves from one part of or one density to another density, it indicates a deviation, it indicates a loss. So overall, if I consider the top 100 meters of water in this region, 100 meter, let's suppose, and if I consider 100 meter of water in this region, let's consider this to be Arabian Sea, and let's consider this to be the region of Bay of Bengal. Now, out of these two, where do you think that the rise of temperature will be very significant? Arabian Sea or Bay of Bengal? Where do you think the rise of temperature in the 100 meters will be very fast? Very good. Bay of Bengal, because all that heat is now restricted to the top portions, right? So here, the temperature rise will be very significant. And when there is a significant temperature rise in the water body, what atmospheric phenomena will it lead to? Very good. You will have the formation of cyclones, tropical cyclones. This is also the reason why, when you consider South China Sea, when you consider Bay of Bengal, you have much more frequency of formation of tropical cyclones, because the top portion of the water will get heated up very, very fast. So hence, the top portion in this case, top portion heats up very quickly, and hence greater cyclones or cyclonic formation. Okay, so now we I hope we have a clearer understanding of all the various factors which will induce a greater formation of tropical cyclones in the region of Bay of Bengal as compared to the Arabian Sea. Okay, so now I hope that when you face a question or encounter any kind of question, any variation in question about why Bay of Bengal has greater formation or greater frequency of tropical cyclones, you will have multiple reasons. Closely surrounded by land, so greater heating, fresh water, hence greater heating. You have the normal conditions of Walker circulation, creating that low pressure in that region. So all these factors, they bring about formation of cyclones in the region of Bay of Bengal. Okay, so after this, we come to the vertical distribution of salinity. How is it that the salinity varies as you move across a depth? So basically, salinity does change with depth. Salinity does vary with depth, because at the bottom, as we have seen with the case of temperature, in the case of salinity also, at the lower portion of the ocean water, the temperature is largely consistent. The temperature is consistent, or rather the salinity conditions is also consistent. Salinity at the bottom is around 35 parts per thousand. Okay, at the bottom the salinity is around 35 parts per thousand. So the variation that you see, variation induced by rainfall, variation induced by melting, freezing, evaporation, all that variation of salinity, that is restricted only to the topmost portion of the ocean. The lower portion of the ocean that is not even impacted by these factors. If there is greater evaporation in certain area, the water at a depth of 4 kilometers will not be impacted by it. So that is why salinity at the ocean bottom is largely consistent, because all the factors that we have seen, they will end up influencing the salinity only at the top and not at the bottom portion. Okay, so whatever will be the salinity at the surface, they will end up varying to gain that consistent salinity of 35 at the bottom, where salinity is consistent. Consistent. Now you can have the variation on the surface. For example, we do know that at the tropics, you have the salinity which is the maximum, close to around 36.5 to 37, right? So here this is 35.5. So salinity at the tropics on the surface will be very high, but at the bottom they have to be around 35. So you will have with depth, as these factors, they don't influence the water at the depth, so salinity will vary. So that zone where the salinity varies from the surface to reach the consistent salinity level at the bottom, that zone of transition of salinity or variation of salinity, this is referred to as halocline. Halo here refers to the halogens or haline, or basically the salt compounds. So here you have the variation in salinity. Again, very quickly, let me recap it. All the various different processes that we have seen, evaporation, precipitation, flow of water, all of that, that is going to influence the salinity only at the top few hundred meters of the oceanic water, not at the bottom. So the bottom largely remains unimpacted by these conditions of melting, freezing, flow, etc. So that is why at the bottom you will find that the salinity conditions, they are consistent, but there's a variation on the surface depending upon the latitude, depending upon the river water, etc. So that means there will be a zone of transition, a zone where the salinity will change depending upon the latitude, and that is the zone which is referred to as halocline in general. Okay, now higher salinity waters is going to be much denser and stays below the water having lower salinity. And higher the density, it will sink much deeper. This property leads to ocean stratification. Stratification is what? Arrangement in layers. So when you have the oceanic water, they are able to arrange themselves in various different layers. That is what is ocean stratification. Why will they be able to arrange themselves in layers? Lower salinity water will tend to float up, higher saline water will tend to stay at the bottom. Here are few of the highest saline water bodies or high salinity water bodies across the world. You'll find Lake Van has got a salinity of close to around 330 parts per thousand, Dead Sea around 238 parts per thousand, Salt Lake in United States a salinity level of close to around 220 parts per thousand. That means in 1 kg Great Salt Lake, there you will find at least 220 grams of salt content. Now, this variation in salinity and temperature of the ocean in between the different latitudes, that in itself brings about a circulation. And that circulation is very, very essential for the circulate or distribution of heat in the oceans, and also for the distribution of various different nutrients that you find in the oceans. Various different species, they depend on the availability of these nutrients. So let us understand that circulation. But before that, a look at the density, the factors of density of water. When we say density, any of us who is not aware about the term density, I hope we are aware of the term density. What do we mean by density? Mass per unit volume gives us an idea about how closely the materials are packed with respect to each other? Isn't it? More density means more materials are packed in the same volume, right? So that is density. Now, density of oceanic water is controlled by two factors. Which are those two factors? Temperature as well as salinity. How? So, temperature, warmer water, when the water gets very heated up, water will end up expanding, isn't it? When the water gets significantly heated up, water will expand. So, what will happen to the density with the rise in temperature? What will happen to the density? Density will reduce, isn't it? So, higher the temperature, lower will be the density, right? So, can we say temperature is inversely proportional to density, right? Or we can actually, the other way around will be more efficient here, that density is inversely proportional. So here, colder water is denser, warmer water is less dense. Hence, colder water is going to be heavier, whereas warmer water is going to be significantly lighter, right? And lighter water will tend to stay at top. Colder water will be heavier, will sink at the bottom. Now, listen to the next 5 minutes very carefully, because that concept will be very relevant even when you consider the current affairs aspects of geography, that is, global circulation and the overturning circulations, etc. Listen to this carefully now. Water with high salinity. Wherever you have very high amount of salinity, that means water is going to be denser, isn't it? That means high salinity is going to be heavier, and low salinity water is going to be lighter, right? Now, consider the region of the tropics. So, in the tropics, the temperature is high. Temperature is high means warmer waters, means ideally lower salinity should be there. But also, we know that in the tropics, salinity is very high, amongst the highest in the tropics. So salinity is highest, means water is going to be heavier. So the temperature factor tells me water should be lighter. Salinity factor tells me water should be heavier. So what do you think will be the density of water in the region of the tropics, or the weight of water in general? So always understand, whenever you have both the factors of temperature and salinity, when both of them are at play, always temperature will be the dominant deciding factor. Whenever you will come across a condition where both temperature as well as salinity they are at play, temperature will always be the deciding factor. Why? Think about it. A water solution which is very saline, upon heating up and heating quite significantly, what will happen? Including the salt content and everything, that water will expand, right? Heating leads to expansion. So that means the salinity or basically the density conditions will be low. So always understand that temperature, when both factors are at play together, temperature decides the density as heating and cooling is going to lead to expansion and contraction. Okay, that is why in the region of the tropics, that is why in the region of the tropics, what do we find? We find that the temperature is very high, salinity is also very high. Tropics has the highest salinity because much higher amount of evaporation, lot of salt content. But despite the fact, the density of water at the tropics is going to be very less. Because of increased heating, it is going to expand ever so slightly, right? So that is a determining factor in terms of salinity and temperature. Now, what does it lead to? Let us understand that. What does it lead to, or why are we so much concerned about this? So, circulation due to temperature and salinity. Now, overall, when we consider the oceanic water, let's consider any of them. Let's consider the Atlantic Ocean for a few moments. So here, basically, let's suppose we consider the water. Now let's assume here we talk about the lower latitude, and here we talk about the polar region. Now, it is almost a no-brainer that where you will have a greater amount of solar insolation and greater amount of heating, you will always find that the lower latitude will have much greater amount of heating. It will have much greater amount of solar insolation which will be received. So what that leads to is the expansion of water, slight expansion of water. Any state of material, when it is heated, tends to expand ever so slightly. So water will also expand ever so slightly when it is heated. So as a result of that heating, water at the lower latitude that expands by close to around 8 to 10 centimeter in terms of height. So here, the water gains a height of around 8 to 10 centimeters higher than the surrounding regions, owing to greater heating. So, greater heating induces expansion, isn't it, of water? That means a height gradient. And we know a property about water, that it will always flow from a greater height to a lower height. I don't think you would have come across any scenario in your life where water from the lower height is moving to a larger height on its own. It is not possible, right? Always it will follow the height gradient. In the polar area, you will find that in the polar region, the temperature is very low. So there is always a factor of slight compression. So the volume of water will be slightly low in the polar region, isn't it? Volume of water will be slightly lower. So here you have a greater height. In the polar area, you have a smaller height. What will that lead to? That will lead to a movement in the water. Water will start to move. because of the height gradient, water will start to move. It will start to move where? Where the volume is very less. There is a height gradient. So water starts its movement. As it comes towards the higher latitudes, it will start losing temperature. It will start becoming colder in the process. It will become very, very cold. And eventually, it becomes colder. It reaches the region of the poles. So as it reaches the region of the poles, water basically becomes very cold. Very cold. When the water gets very cold, what will happen to the salinity in this case, or rather density in this case? Density increases. Also, in this area, around the polar area, you will also experience that because of very cold conditions, there will be more freezing. So, more freezing means what? More freezing. Wherever you have more freezing, what happens to salinity? Salinity increases. With the increase in salinity, what happens to density? Density also increases, isn't it? So, as the water reaches the polar region or the higher latitude, the density increases. Means what? Water will become heavier. And when the water becomes heavier, what will happen? It will sink. It sinks here. Meanwhile, in the region of the lower latitudes, that is in this region of the tropics, here the top portion of water has flown away. It has basically started flowing. Now, there will be more heating, more expansion, more flow away. So, in a way, here you will observe what? That water from the lower regions, they are rising up, expanding, and then flowing away. Now, that means there is a kind of a gap here, a vacancy created, and here you have a kind of a surplus. So, as a result of this, water will end up having a kind of a flow towards the lower latitudes in subsurface, right? Subsurface movement towards low latitude. Now, this induces a circulation in the ocean water, and that circulation is initiated. Why? Because of differences in temperature and salinity. The differences in temperature and salinity, they will induce this circulation. And that is why this circulation is what is also referred to as the influence of temperature, hence thermo, influence of salinity, hence haline circulation. That is what we refer to as the thermohaline circulation, where on the surface, water will move from lower latitude to the higher latitude. Subsurface, water moves from higher latitudes back to the lower latitude in order to have the, or this is particularly driven by the difference in density. And that is created or influenced by the difference in terms of the temperature and salinity conditions. So that is why here you will observe this is what is referred to as the thermohaline circulation. Thermohaline circulation. Okay, so denser water tends to sink at the higher latitudes, whereas lighter water rises up at the tropics or at the lower latitudes because of very high amount of heating. So high amount of heating, what it does is, the high amount of heating, again very quickly I will recap, high amount of heating in the lower latitude will lead to expansion of water. So water ends up gaining a kind of a height gradient, a height advantage of 8 to 10 centimeter as compared to the water from the higher latitudes. So that in height difference initiates a kind of a flow from a lower latitude to the higher latitude. And when water reaches the polar region, not only will the water become cold, cold means heavier, but also salinity will increase. So both of these conditions makes the water heavier, water sinks down, and that is when the entire circulation is achieved. Okay, right? And why temperature factor prevail over salinity factor at tropics? Anywhere, if you consider, temperature factor will dominate over salinity, because see, what is it that the temperature will bring about? The impact of temperature. Impact of temperature will bring about the expansion and contraction. This will either expand or it will contract. Whether you have salt content in it or not, it will expand, right? The matter will expand and will contract. So that is why it becomes a more predominating factor. And uh, Varun, you had a question that stratification phenomena occurs only in the tropics in significant proportion. Yes, it is more predominant in the tropics. In the region around the portion of the poles, there you don't have that much stratification which is observed, but the formation of less dense water can create stratification there also. Okay, right? I hope that is understood. Now, why is subsurface water moving from polar region to the lower latitude? Because from the lower latitude, the water has been rising up, expanding, and moving away. So some portion of the water needs to fulfill that vacancy. So that is why water comes from higher latitudes. Okay. Now we come over to the movement observed in the ocean water. So we come to the portion of tides and waves. This may cause of water circulation and not in air. Water circulation. How is this? Okay, the entire circulation is similar to that of convection cell in the air, but to have a similarity with Walker circulation will be improper here. It is found in upper layer of the ocean only? Yes, significantly around up till 2 kilometers, three. Sometimes in certain oceanic water, as we'll come to the global ocean conveyor belt, we find out that it is observed even in much greater depth also. Variation in density, which leads to stratification, is due to more rivers discharging water in Bay of Bengal. Yes, Pulkit, that is correct. Okay, this would happen in both the hemispheres. Alok, yes. If you want to have an overall look, I'm not talking about the global circulation right now. I'll however show you the shallow. That is what I told you. It is mostly found in the upper portion of the ocean only. In certain oceans, it is found to the lower depth also, but in majority of the cases, it is found in the upper portion only. I think unless and until the name is called out. So here, I want you to take a look at this particular portion. Observe. This is nothing but a large scale thermohaline circulation. A large scale thermohaline circulation where you will observe that water in the polar region, they will they will sink and they will rise up in the tropics after getting heated. That is something that you find here. We'll come to it in more greater detail when we come to the portion of movements. Okay, so movements in ocean water. The ocean water is basically going to experience some or the other kind of movement initiated and induced by the various factors. Okay. Um, but these two things are contradictory at tropics: high temperature, lighter water; high salinity, heavier water. Then water will be heavier or lighter. Hmm. So I think you would have missed out this entire concept when we were talking about this, and when I had written all of this, I think you would have completely blanked out at this point of time, because here we have written at the tropics, when both are together, temperature decides the density. Even though it is contradicting, the temperature decides the density. Okay, we have talked about it in significant detail, why temperature decides density. Now, coming to the portion of tides and waves. So, we start first of all with the basics of waves. Waves are not going to be very relevant for your examination in general studies, because in general studies, you are not required to go into the depth of these waves. That what is the wavelength, the relation between the wavelength and the depth of the waves, that is something which is not required for general studies. So, not many questions are framed from here. But here, first of all, when we talk about the waves, how is it that the waves are created? Or what do you think is the factor which leads to the creation or the formation of the waves? So, the waves in general are created by the influence of winds. Very good. Not gravity. Influence of winds, and winds only. Now, what happens is that when you have the winds in general, right? So, in general, if you have ever observed the wave not at a coastline, but let's say you have gone few meters or 100 meters into the water, you would observe that water basically rises up, falls down, rises up, falls down, right? There not much of a forward or a backward motion. So, what happens is that here, if you have the water, let's suppose, and the wind is blowing on top continuously. Now, what this wind will do is it will try to carry some amount of this water along with itself. But obviously, it will have its limitation. It will not be able to carry this water endlessly. So, this water will drop. Meanwhile, the other portion will also be carried by the wind. It will also drop. When it will drop, it will try to regain its natural position. Right. So, wherever you have that significant rise, that results in a kind of a wave like formation. Wherever that water is dropping, you will have a kind of a trough. Wherever that accumulation is happening, you will have a kind of a crest. So, overall, if you observe the movement of the water during the waves, the water does not end up moving forward or backward. Water ends up remaining where it is. And here, the motion that is observed being carried by the wind or carried by the waves in general, water is carried, it is dropped, and the region which was a crest earlier then gets converted into a trough, and vice versa is also true in that case. So this is basically the formation of the wind or the wave. Now here, what is the motion observed in the particle, the individual particle? How is it that the individual particle ends up moving? So each individual particle, you will find that they will move in a kind of an oscillatory motion. They will be moving in a kind of oscillatory motion. Right? So they will be staying in that same place. They will be brought up by the wind. They will be dropped by the wind, again brought up, again dropped. And that is how you have the waves. Now, here you might have a question. If you are saying that the waves are nothing but the variation of water there itself, then why is it that in the coastal areas we experience the waves to be coming in and then going back? Are they not waves? So there also you have the occurrence of waves, and the same principle is observed. So if you have the water, and if you have, let's say, the coastal region, now Here also the wind will carry the same process. Water rising up, water falling down. But in this case, water will not be able to fall down to the same extent that it rose up. And meanwhile, wind will start raising up the water next to it. So what do you observe here? You will observe a kind of a piling up of water, isn't it? For temporary duration itself, water will start to pile up. And that is what you observe in this formation that you see in the form of waves. This is being brought by the winds, water is piling up. So, as a result of this, what happens? Water comes forward across the coastline, right? And you would have observed when you stand across the coastline, you would have observed that water comes to you and then goes back. Why does the water go back? Why will the water ever go back if it has come up? That is, first of all, aided by gravity, the slope, and secondly, the water will try to complete its rotational motion. The particles will try to complete its entire rotational motion. So, all that piling up will have a movement back also. That is why, during the case of the waves, water comes inland and then moves backwards. That forward movement of water across the coastline, when the wave comes and enters into the coastal area, and then again it goes back across the beaches. So that is what is referred to as swash and backwash. And backwash. This is the forward movement of water. Forward movement of water. And this is basically the water coming back to the sea or ocean. So you would have observed this, or at least seen in the videos and the movies, that when you stand across the coastline, water comes towards you and then goes back. When the water comes towards you, swash. When the water goes back, that is backwash. Now, many of the times, people get confused and they end up using waves and tides in the same proportion, meaning the same thing. But tides are very different when you compare them to the waves. Okay, tides are going to be significantly different. So when we talk about tides, tides basically mean that water will have a vertical rise or fall. The water level rises up and falls down almost twice a day. That is what you consider as tides. Now, why does that happen? You have multiple factors which are involved here, but the basic factor is the gravitational pull of the sun and the moon, and also the centrifugal force. That is something that we are going to look into. But as a result of this, water tends to rise up, water tends to fall down, right? And that is what is referred to as a high tide and also a low tide. Okay, so the major causes: gravitational pull by the moon and the sun. Even though the sun has got a very large mass, but still the influence in terms of tides is largely subtended by the gravitational pull of the moon. And why is that? Because moon is much closer to the earth. Because moon is much closer, hence you will have greater influence of the gravitational pull of the moon due to proximity. Okay, hence you will observe a greater influence in terms of the gravitational pull, right? Now, in this situation, when you consider, let's suppose, the planet. let's consider the water surrounding that planet. Let's consider water surrounding that planet. Let's consider the moon. Okay, this is the moon. This is Earth. And this blue ring, that indicates the presence of water all around. Now, moon will exert a gravitational pull of attraction. So while the gravitational pull of attraction will be nowhere as strong to pull the planet in itself, but it will be strong enough to influence the water which is present. So here, water will experience a kind of a piling up. Water will experience a kind of a piling up, isn't it? Because of the gravitational pull of the moon. Now, where will this water come from? Will the planet suddenly start pumping out more water? No, this water will come from the sides here, from here. Right? Now, on the opposite side, in order to maintain the balance, or as the planet is rotating, in order to maintain balance, the opposite side will develop a kind of a counter bulge. That will develop a kind of a counter bulge. Right? In order to maintain balance, in order to have the momentum to be conserved, it will develop a counter bulge on the opposite side also. So all around the latitudes or the longitudes where the moon is exposed, you will find a bulge and the water would be taken from the surrounding areas. So what do we observe in terms of water level? You will observe that in two areas, water level has increased, isn't it? Whereas in two other areas, water level has substantially reduced. So the region in which the water level has increased, that will be what? A high tide. The region where the water level has reduced, that will be what? A condition of low tide. But the moon also ends up moving around the earth. So let's say the moon basically is present here. Let's suppose moon has come over to this region. Now what the moon will end up doing is forming a bulge somewhere here by taking water from the sides in this region and then forming a counter bulge in order to maintain the equilibrium, right? So now the region which had experienced a low tide, there the water level has increased. That region will experience high tide now. Whereas the regions which were experiencing high tides, there the water level has decreased. That will experience low tide now. Then again, moon, let's say, comes here, right? So again, the first conditions will revert. Then the moon will come here. So that is how, as the planet rotates, the influence of that gravitational pull will end up extending across the planet. That is why, in general, you come across the fact that you have two instances of high tide and two instances of low tide experienced during the day. The planet in itself is also rotating around its axis. So each and every part gets exposed to the moon and the gravitational pull of the moon, right? That is why what you experience is that every day, if you notice, if you are living in a coastal area, you will be very much familiar with it. But the next time when you go to the coastal area, observe this. that every day in the morning, 6 a.m., you have a condition of low tide. Then around 12 p.m. in the afternoon, you have the condition of high tide. Then again around 6 p.m. in the evening, you have the condition of low tide. And again around 12 a.m. in the night, you have the condition of high tide. That is why you'll find that the basic guards who are posted or who are positioned at the beaches, they will start evacuating people from the water around 12 or 1 p.m. because it is a condition of a high tide. Water level suddenly increases, right? So that is how basically you have the formation of the high tide and the low tide which you experience in general. Okay, so a schematic representation of this, observe this as the ocean, the moon. Moon will create a bulge. There will be a counter bulge developed to maintain the equilibrium as the planet is consistently moving and rotating. So all areas around that will develop that bulge eventually in order to maintain that counterbalance. And that is why in these areas, where do you get the water from? Water, that excess water is going to be supplied from the nearby adjacent regions. So there you have low tide. And in these regions, you will experience high tide conditions. But here, you also have an influence played by the centrifugal force. What is this centrifugal force? When we talk about centrifugal force, what is it? So, whenever any object moves in a circular motion, there is a force acting on the outside direction. And that force acting on the outside direction is the centrifugal force. So take a string and a ball attached at the end of the string, start rotating it with significant velocity. After a point of time, you will experience that the string or the ball tries to move away from you. That is the force acting away from the center. That is the centrifugal force. So in the case of the planet Earth and its rotation around the sun, there also you have the centrifugal force which is acting. How? So let's suppose we consider the sun, okay, and you have the orbit of the earth around the sun. You have the orbit of the earth around the sun. Now the earth moves consistently around the sun along the orbit. Now as the planet continues to move in a circular path, there will be a centrifugal force acting on the outside. Now, while that centrifugal force is nowhere strong enough, this is the sun, this is the earth, just so that nobody confuses it with a Saturn ring. So this is the sun, the earth, and the direction of the centrifugal force. So this centrifugal force, which is acting in the outward direction, it will tend to push the water. It cannot push the entire planet. It will nonetheless push the water. So that is why here you will find a kind of a tidal bulge developing here also, right? So overall, observe in very simple terms that the gravitational pull will create a bulge, the centrifugal force will create another bulge, and eventually both of them together will have a cumulative impact of creating two of these bulges, right? Which means two areas will have high tide at any point of time, and two regions will have low tide at any point of time in general. Okay, so that is basically the causation. Now you have classification of tides. Based upon how it is formed, why it is formed, and when it is formed, you have the classification. Now we have seen that the role played by the sun and the moon both are vitally important. However, moon will have a greater influence in terms of gravitational pull because moon is much closer. So here if you analyze, in front of your screen you have two images. As of now, I know it is incredibly difficult. As of now, ignore the second image and focus only on the first image. The first image. And look at it very carefully. When you take a look at the first image, you will observe that the sun, the earth, and the moon, they are on the same plane, right? You will observe that the sun, the earth, and the moon, they are on the same plane. So that position, first of all, when they are on the same plane, that position is referred to as syzygy. When all of them are on the same plane. Now in this also, you can have a situation where moon is on the opposite side of, and moon and sun, they are on the opposite side of the earth. For example, this one that you observe on full moon. Moon is on the opposite side of the sun. This is a position which is referred to as apposition. Whereas here, when the moon and the sun, they are at the same side, that is referred to as conjunction. Okay. Now, in both these cases, further if you observe the image, you will observe a small image here, a small bulge here referring to solar tide, and another larger bulge here referring to the lunar tide. I hope you are able to see this. That basically means the impact by the sun, the impact by the moon. Now, when they are on the same plane, the impact by the sun, the impact by the moon, they will add up, right? So they will add up. So what does that mean? The bulge that is created is going to be humongous, is going to be very, very high. So that is, in that condition, what will be the case of high tide? Will it be normal? No, it will be higher than normal. Normal high tides, very high. But for every high tide, you are required to get water from the surrounding regions, isn't it? So, then what about the condition of the low tide? In the condition of the low tide, what do you think? Low tide will be as the case with all the normal low tides, or will the low tide also show a variation? Apply your logic here. If the high tide is higher than average, what will happen to the low tide? Beautiful Deepika. Lakshmi, good. Pulkit, good. Dipesh, good. So here, low tide will get lower than average. Why? Because all that water will be required to fill up that high tide. So there you will observe lower than average low tides. Isn't it? So these conditions will be experienced twice a month. Moon takes around 28 days to complete one movement around the earth, right? So in those 28 days, you will experience it twice. Whenever moon, earth, and the sun, they are across the same plane. Now, this is a condition which is referred to as the spring tide. Observed whenever you have a new moon and whenever you have the condition of a full moon. That is what is a spring tide. Now, moon takes 28 days to complete one rotation. That means in around 1/4 of the time, 7 days, it will come perpendicular, then again 7 days, then again 7 days, again 7 days, one complete rotation. So when after 7 days, moon comes in a position perpendicular to the plane of earth and sun, this is a position which is referred to as quadrature. This is what is referred to as quadrature positioning. Observe here, observe the case of the solar tide. Observe here the solar tide, the bulge created by the solar tide. And observe the bulge created by the lunar tide due to the position of the moon. Now, in this situation, now tell me, high tide, will it be same, higher, lower? What will be the condition of high tide in this case? Quadrature is the position when the moon is perpendicular to the plane of earth and the sun. Very good. In this case, you will have the solar and the lunar tide will cancel each other out. So that is why high tide will be lower, right? In comparison. Whereas, what about the low tide? When we talk about the low tide, in general, low tide basically is created as the water is supplied to the regions accumulating the high tide. So that is why low tide, because the high tide is lower, low tide in general will be higher. You don't have that much water which is going to exit, so higher in comparison. So this is a condition which is referred to as neap tide. So after every 7 days, you have a variation from a spring to a neap tide, to a spring tide, to a neap tide, again to a spring tide. Okay, so that is basically the variation. Now, here the spring tide. When the sun, the moon, and the earth are in straight line or the straight plane, height of the tide will be higher. Why? Because the solar tide and the lunar tide will add on to each other. So that is where the height of the tide will be higher. They occur twice a month, one on a full moon period and another during new moon period. And when the sun, the moon, and the earth are in the same axis and the same line, that is a position referred to as syzygy. And in this syzygy also, you have two positions. Conjunction, when the moon and the sun are on the same side. So here, this is a position where the moon and the sun are on the same side of earth. That is conjunction. And opposition, when the sun and the moon are opposite to the planet. That is opposition. In both these cases, the solar tide and the impact of the moon will add up. Solar and lunar tides will add up. Okay, so high tide will be much higher. High tide is much higher. Whereas after 7 days of a spring tide, you have the condition of a neap tide. And neap tide is the interval between spring tide, or you have a 7 days basically. So here the sun and the moon are at right angles to each other, and the forces of the sun and the moon, they tend to counteract each other. So this basically, this position is what is referred to as quadrature. Position is quadrature. Okay. And after that, the moon's attraction, though more than twice as strong as the sun, is diminished by the counteracting force. That is why you have those basic events. Okay, that is the condition of high tide and neap tide and spring tide. Now, overall, if you take a look at the basic characteristics, you'll find that in the region of wide continental shelves, where the shelves are very wide, the impact of the tides is very significant. So, for example, let's suppose you have a condition of the coastal area where the shelf does not have very steep gradient, has got a very gentle gradient, and the shelf extends quite significantly. Now, let's suppose the normal water level, let's suppose, is here. Now, during low tide, if the water level reduces ever so slightly, the level of water will come somewhere here. During high tide, if the water increases substantially or even in limited proportion, what do you observe? Observe where the water goes. So, during the high tide, the water will end up covering significant portion. So, this is the what is referred to as the high tide line. And this is what is referred to as the low tide line. Isn't it? So, this is the variation or the distance between the high tide and the low tide. And that can be very expansive in the case of flattish beaches. For example, in Odisha, you have the Chandipur beach. And at the Chandipur coast, you will observe that water retreats quite significantly during the low tides, where all the various shack owners, restaurant owners, they will set up their tables and chairs, and you will be served the snacks. And as soon as the high tide comes, everybody vacates it. So water can retreat few kilometers and come back a few kilometers due to variation in height depending upon the continental shelf. Continental shelf also, in a way, owing to the shape of it, sometimes ends up magnifying the impact of the high and the low tide. Right? So example of this, Chandipur in Odisha. UPSC has asked this question in the prelims 2017, that which place in India experiences such a wide variation in terms of the high tide and the low tide. Now, the shape of the coastline also ends up influencing channelization of water in large bulk, eventually creating significant rise and fall. For example, I had asked you to locate the region of Bay of Fundy. Observe the region of Bay of Fundy on the map again. Where is it? Northeastern part of North America, near Nova Scotia. So, Bay of Fundy, you will observe one of the greatest variations in terms of tidal height experienced there because of the shape. As there is a rise, more water is being channelized into the inlet, and hence within the inlet, you'll find much greater variation. These tides help in navigation. You will observe, if you are living in a coastal area or if you have been to a coastal area, you will observe early in the morning, right, that you will observe that the fishermen, as there is still the condition of the high tide, they will be able to take the water, or they will be able to take the boats into the water, because that high level will allow them to carry out navigation much easier. Right. So that is why you'll find the fishermen leaving either late at night or early in the morning in order to go to the deeper portions. So sometimes the high tide and the low tide also induces a flow of water. For example, if you consider, this is the last example I'll talk about, and then we will end the session here today. So, for example, if I talk about a land area, let's suppose somewhat like this. Here you have sea, here you have land, here also you have land, the top view, right? And let's say the cross-sectional view that I give you is somewhat like this. You have sea, and this is the portion A, let's suppose. Now, if water level is here, During high tide, what you will observe? During high tide, water level will increase. So all that water will straight away rush in. Water will rush in here. And during low tides, what we will experience? Here, the water level will reduce. By this time, water would have filled here. So all that water will rush back. So this movement of water is caused because of tidal variation. That is tidal current. Okay. So that is the characteristic of tides. And that is where we'll restrict the session here today. We meet again tomorrow. That is when we'll finish the portion of oceanography and we enter into the portion of Indian geography finally. Okay. So now I'll take few questions, as many questions as I can. But the questions that I'm unable to take, please don't worry. The SMEs are here. They will get back to you. Will it cause fjords? Sachin, fjords are created as a result of erosional action by the glaciers. The fjords that you see in the region of northern part of Europe, North Canada, they are created by action of erosion. Shalu, but moon and earth in opposite direction, then how 2 point you have written correct? Which 2 point I have written? Where are you asking about 2 point? Uh, Moon and earth are in opposite, high tide and low tide. Understand one basic thing. First of all, understand the basic thing. When the moon, earth, and the sun are on the same plane, the gravitational bulge or the tidal bulge created by the sun and the moon, they will add on to each other. So when they will add on to each other, means what? The bulge created will be much higher, right? There will be cumulative impact created. So the bulge created will be much higher. Now, the bulge created much higher, I hope that is understood why. But if there is a higher bulge created, where do you get that excess or extra water from? In order to have the rise in water, let's say in central Atlantic, you need that water from somewhere. Where will you get that water? Suddenly, do you think that Atlantic will start producing more water, that now moon is there, we have to produce more water? No. You will have that water coming from the other areas, isn't it? So what does that create? That creates a kind of a low tide in that region, much lower than average, because all that water needs to be supplied to the tidal bulges which have been created, which have been added up, isn't it? So low tide is formed where? Low tide is formed here. Low tide is formed here. So low tide is, on the average, will be lower in comparison. Okay. And Ashwant, during the cyclone, uh, time, the wind gushes towards the land, and here the waves crest will be high and difficult for navigation. And this leads to disaster like entering into the land that is near. Is this dependent on the wind speed? Absolutely, yes. That is what brings about storm surges. Uh, Then in neap tides, why does lunar and solar tides cancel each other? Rahul, that is because in the neap tide, if you observe, look at the solar bulge. Solar bulge will be very similar both in the spring and the neap tide, because the position of the sun and the earth, that is consistent. But this time, because the moon is perpendicular, the tide will be created like this. So that is why the portion of the bulge here will coincide with the portion of low tide of the solar bulge. So that is why they will cancel out each other. And Pulkit, Since in every 28 days there will be two syzygy instances, but still eclipses are seen rarely. That is because it is not always going to be on the same line. It can happen that you have the sun, you have the earth, you have the moon. They are in the same plane. The gravitational pull will be added on in both these cases. Okay, that is why. Uh, Sumit, what will happen to in the first quarter moon and the third quarter or the third quarter moon? Neap tide, it will cancel out. You will have the impact of each other being cancelled out. Uh, Anthony, when the Earth is between the Sun and Moon in opposite phenomena, does Earth not impede the gravitational force of Sun and Moon? No. Why will the Earth impede? Imagine if the Earth is in between the Sun and the Moon, both of them will try to pull the planet. And as a result of that, both of them will create a significant bulge at the same plane. And because it is created at the same plane, both the bulges will keep on adding to each other. That is why a much higher high tide and a much lower low tide. I hope that is understood, Anthony. Priyanka, river discharge adds ions and river flows decreases salinity. Again, I would come back to the very basic concept. Priyanka, you had the simple question, a similar question that groundwater has minerals. So how come groundwater reduces salinity? And it is in response to that I had told you. Look at the net addition. The seawater, the river water adds ions. But if it is adding, let's say, 3 grams of ions, it is adding 30 kg of water along with it. So in net or in total, what is the addition? There is an addition of what? Water in general, isn't it? So that is why you will have a greater addition of water. And sun is responsible for centrifugal force and the moon is responsible for the gravitational. Both of them are responsible for gravitational force. Um, but in case of spring tide, earth, moon, sun in one side and forces in one side. So okay, so this is basically the same question that you had, um, that why is it that a bulge develops on the other side also? Here you observe this is the position of the moon. Why is it that a bulge develops on the other side? I think that is the gist of your question. So basically here you will observe that not only will you find significant amount of gravitational bulge created in this area, some portion is also attributed to the centrifugal force for the bulge created on the other side. But also understand that water is taken from these areas and the planet is consistently rotating as well. So it is not going to be, if let's say you consider this as a spherical plane, it is not going to be that a bulge is created only across one and nowhere else. Across the entirety of the latitudinal extent in that region, a bulge is going to be formed in order to maintain a kind of a counterbalance. Right? For example, in the planet itself, the planet is a large sphere. In one area, if you keep on piling things, you will have a counterbalance or the counter effect on the other side. So it is that counterbalance, the maintenance of the momentum, the inertia, that is why you have a counter bulge which develops. So that is why the counter bulge develops. So even if, let's say, the moon is here or the moon is here, you will have the bulges developing on both the extent. Okay. Okay. And I hope that is understood. Then please try to make sure that the team will upload the annotations of the PPT around 10:30 a.m. Okay, that is something which is generated by the software itself, the annotations. Sometimes it will take half an hour. Sometimes it takes more than 2 to 3 hours also. So we will try our level best to upload it as soon as possible. Yes, Jay, Biparjoy is in news because the new cyclonic circulation. In neap tides, normally there is a 7-day interval between spring and neap. At this time, the sun and the moon are at right angles to each other, and the forces of the moon tend to counteract. Yes. All that is correct, Rahul. Pulkit, although the cause is different, but the effect of both tides and waves remain the same, resulting in motion of water. Yes, but tides have a much substantial impact in terms of increasing and reducing the height that the water has. Okay, and Siddharth means when the moon completes one rotation around the axis, that is around basically 28 days. Okay, and eclipses are rare because, see, eclipses will happen when 3 points occur across the same line. So that is why it is very, very rare. Okay. Lakshmi, you can read any of these. You can read for your revision purposes. Shalu, neap tide. Shalu, have you understood the problem that you had asked first of all? That problem, is that clear, that why in the case of opposition as well as conjunction, why will you have the condition that neap tide is going, the low tide is going to be lower and high tide is going to be higher? First, let me know that. Okay, good. And then your other question is neap tide, lunar tide. Neap tide, lunar tide is higher. Answer, solar tide is lower. I'm unable to make sense of this. I apologize for this. I am unable to make sense of this. Kindly clarify. See, Sonam, this symbol is an indication of parts per thousand. Percentage, how do you indicate? By this. Parts per thousand, you include two zeros or two dots at the bottom. That is parts per thousand. Okay. And centrifugal force in tide formation, ocean, is very simple. As the planet rotates or moves around the sun, it will experience a force on the outside, and that creates a tidal bulge that is referred to as the centrifugal force. Okay, right? Can we say temperature and salinity are directly proportional? No, we cannot make a conclusion like that. Only in tropical regions. Okay, still we cannot make a conclusion like that. Because you have variation in terms of the latitudes. Um, Lunar tide is higher, whereas solar tide is lower due to low gravity. Yes, that can be a conclusion made, Shalu. Yes. So that is where I'll end the session here today. We meet again tomorrow, and tomorrow is when we enter into the portion of Indian geography. So till that point of time, revise, take care of yourself, relax, and see you again tomorrow. Goodbye. Thank you.